Hello and welcome to Sleepy Science. What if I told you that the world around you is not as quiet, solid, or empty as it appears? That invisible forces are moving through your body right now. That empty rooms are filled with hidden motion. That matter is mostly open space. That light can push without hands. Sound can shape sand and water. Magnets can reveal invisible fields. And even dust floating in a sunbeam can expose secret rivers of air. These are not myths, illusions, or fantasy explanations. They are real pieces of hidden science woven into ordinary life. The physics of shadows, lightning, smoke, bubbles, snowflakes, ice, friction, heat, static electricity, and the strange structures hiding inside materials we touch every day. Over the next 4 hours, we'll move gently through 30 quiet mysteries that make the familiar world feel unfamiliar again. We'll explore why cracks follow hidden stress maps, why smoke rings hold their shape, why foam is secretly structured, why water can climb against gravity, why ferrofluids grow dark magnetic spikes, and why water behaves like it has a memory, but not in the way myths often claim. So, if you're ready to stop seeing the ordinary world as simple background and start noticing the invisible rules, hidden forces, and silent patterns working beneath every surface, tap like, hit subscribe, and step into the hidden science all around you, where even a shadow, a snowflake, a spark, or a drop of water can make you question the world you thought you knew. The invisible forces moving through your body right now. Your body is not a sealed container moving through the universe. It is a soft, living crossroads where unseen forces arrive, pass through, push, pull, guide, and disappear before your awareness can name them. Right now, even if the room feels silent and nothing around you seems to move, your body is being shaped by pressures, fields, vibrations, chemical gradients, electrical impulses, and tiny exchanges of energy that never pause. You experience this as ordinary life because your brain hides most of the machinery from you, giving you only the simple version: weight, warmth, breath, heartbeat, touch. But beneath that calm surface, physics is happening everywhere. Gravity is pulling every part of you toward Earth. Not only your bones and muscles, but also your blood, your organs, and the fluid inside your inner ear that helps you understand balance. Your body has spent a lifetime learning how to live under that pull, which is why standing upright feels normal instead of astonishing. Your skeleton is not just a structure, it is a response to the planet. Your muscles are not just for movement. They are constantly making small corrections so you do not fall. Even when you are still, you are quietly resisting collapse. Around you, air presses against your skin like an invisible ocean. You do not feel its full weight because your body pushes back from within, but every breath depends on this pressure. When your chest expands, air enters because pressure changes, not because the lungs magically pull it in. The atmosphere flows into you, gives oxygen to your blood, then carries away carbon dioxide when you exhale. Breathing is not just biology. It is the outside world becoming part of you for a moment, then leaving changed. Inside your body, another invisible force is constantly speaking. Electricity, not the violent electricity of a storm, but the delicate biological electricity of nerves and muscles. Your thoughts, reflexes, heartbeat, and sensations depend on charged particles moving across cell membranes. A memory, a blink, a shiver, a sudden feeling in the stomach. All of these rely on tiny electrical changes traveling through living tissue. Your heart beats because specialized cells create repeating electrical signals that tell the muscle when to contract. Your brain feels like a private inner world, but it is also a living field of electrical communication. Then there are the molecular forces holding you together. The atoms in your body are not locked in place like bricks. They are held by attractions and repulsions between charged particles, and these interactions help create the feeling of solidity. When your hand rests on a table, the atoms of your skin do not truly merge with the atoms of the surface. They resist each other. Your nerves translate that resistance into touch. What feels like direct contact is really the body reading invisible boundaries. Heat is also moving through you at every moment. Your cells produce warmth as they use energy from food. Your skin loses heat to the air. Blood carries warmth from your core toward your surface. When you sweat, evaporation takes heat away. When you shiver, muscles create extra heat. Comfort is not passive. It is a balance your body is constantly defending. Even light participates in this hidden conversation. Light enters your eyes and becomes vision, but it also helps regulate your inner clock, telling your brain when to feel alert and when to prepare for sleep. Sunlight can help your skin begin making vitamin D, while too much ultraviolet light can damage cells. Light is not just something that reveals the world, it is something your body responds to chemically and biologically. Sound moves through you as pressure waves. A voice becomes vibration in the air, movement in the eardrum, motion in tiny bones, waves in inner ear fluid, and finally electrical signals in the brain. That means every word you hear begins as physical motion before it becomes meaning. Even silence is not truly empty, because your body continues to hum with blood flow, nerve activity, breath, digestion, and the faint internal noises your brain usually filters away. And beyond Earth itself, traces of the wider cosmos pass through and around you. Particles created when cosmic rays strike the atmosphere can reach the ground. Neutrinos from the sun stream through your body in enormous numbers, almost never interacting with anything. They do not control you or carry mystical messages, but they remind you of something humbling. You are not separated from space by walls, ceilings, skin, or thought. You are inside the universe, and the universe is quietly passing through. The deeper truth is that your senses do not show you reality as it fully is. They show you the version useful enough to survive. If you felt every air molecule, every tiny electrical shift, every temperature exchange, every microscopic collision, every particle passing through, consciousness would become impossible. So the brain simplifies the storm. It turns vast, invisible activity into a calm human experience. And maybe that is why this subject feels so strange. Nothing supernatural has to be added for the world to become mysterious. The real world is already more intimate, more active, and more astonishing than it appears. You are being pulled by a planet, pressed by an atmosphere, powered by electrical signals, held together by molecular forces, warmed by chemical reactions, touched by light, moved by sound, and crossed by particles from the sky. So when you sit quietly and think nothing is happening, remember that stillness is only the surface. Beneath it, your body is participating in a hidden physics of being alive, and every breath is proof that the invisible world has never stopped touching you. Why empty rooms are never truly empty. An empty room only looks empty because your senses are too slow, too limited, and too human to notice how crowded silence really is. You open a door, step into a quiet space, see no people, no movement, no obvious life, and your brain gives you a simple label: empty. But the room is not empty at all. It is filled with air molecules racing in every direction. Dust drifting like tiny weather systems. Water vapor floating invisibly, smells left behind by paint, wood, fabric, cleaning products, and human skin. Microscopic organisms resting on surfaces. Light bouncing from wall to wall, heat radiating from objects. Radio waves passing through the walls, and faint vibrations too weak for your ears to notice. What you call emptiness is really a failure of detection. The room is full. You just are not built to see most of what fills it. Begin with the air itself. In a room that seems completely still, the air is not still. It is a crowded sea of nitrogen, oxygen, carbon dioxide, argon, and tiny traces of other gases, all moving constantly. Each molecule is too small for your eyes, but together they create the atmosphere inside the room. They collide with each other, with the walls, with your skin, with every object on the table. If you could suddenly see the air at the molecular level, the room would not look calm. It would look like a blizzard of motion, a wild, invisible storm happening in every direction at once. Yet because the motion is so evenly spread, it feels peaceful. This is one of the quiet tricks of reality. Disorder at a tiny scale can become calm at a human scale. The same room also contains humidity, even when the air feels dry. Water molecules are floating through it, leaving surfaces, returning to surfaces, gathering or thinning depending on temperature and ventilation. That invisible moisture matters. It changes how comfortable the air feels, how quickly sweat evaporates, how wood expands or contracts, how dust clumps together, how static electricity builds, and how long some tiny droplets can remain suspended after someone speaks, coughs, or breathes. A room remembers presence in physical ways. Even after a person leaves, traces remain. Carbon dioxide in the air, microscopic skin flakes in dust, fibers from clothing, oils on door handles, and scent molecules slowly fading from the space. Smell is especially revealing because a smell is not an abstract quality floating in your mind. It is matter. When you smell fresh paint, old books, coffee, perfume, rain on clothing, or a closed room that has not been aired out, you are detecting molecules released into the air and caught by receptors in your nose. The room is telling you what has been there, what materials it contains, how recently it was cleaned, how much air has circulated, and sometimes even whether mold or dampness may be present. Empty rooms carry history in chemistry. They do not speak, but they leave clues suspended in the air. Dust is another hidden population. It is not just dirt. Household dust can include fabric fibers, pollen, soil particles, tiny fragments of skin, bits of paper, soot, minerals, insect debris, and microscopic plastic fibers from synthetic materials. It moves with air currents so faint you may never feel them. A warm laptop, a sunlit window, a person walking past, or a door opening can create tiny flows that lift dust, carry it, and lay it down again. In sunlight, you sometimes see dust sparkle in the air, and for a moment the room reveals what was always there. The beam of light does not create the particles, it exposes them. That is often how science works. It does not make the hidden world strange. It gives you a way to see the strangeness that was already present. Surfaces too are less empty than they appear. A clean table may still hold bacteria, fungal spores, oils, salts from skin, and residues from whatever touched it before. Most of this is harmless in ordinary life, and many microbes are simply part of the background world we share. But their presence reminds you that cleanliness is not the same as absolute emptiness. A room can be tidy and still biologically active. It can be silent and still chemically changing. It can seem frozen while its materials slowly age, release compounds, absorb moisture, fade under light, or respond to temperature. Even the walls are not passive. Paint, wood, plastic, carpet, and furniture can release tiny amounts of volatile compounds, especially when new, warm, or poorly ventilated. That new room smell, that old house smell, that closed-up heaviness after a long absence, all come from matter interacting with air over time. And then there is radiation. Not in the frightening sense people often imagine, but in the ordinary physical sense that objects constantly emit and absorb energy. Every object in the room with warmth gives off infrared radiation. You cannot see it with your eyes, but thermal cameras can. A chair, a wall, a blanket, a cup, your own body if you're inside the room, all glow in infrared according to their temperature. The room is quietly exchanging heat with itself, surfaces sending and receiving invisible energy until balance shifts again. This means stillness is not the absence of activity. It is activity so balanced that it stops calling attention to itself. The room may also be crossed by human-made electromagnetic waves, radio broadcasts, mobile signals, Wi-Fi, Bluetooth, television transmissions, and other signals moving through space. They do not make the room magical, and at normal exposure levels, they do not mean the air is dangerous. They are simply part of the modern, invisible environment, carrying information through a space that your eyes describe as blank. A phone can receive a message in a room that looks empty, because emptiness, to your eyes, does not mean emptiness to physics. Even if you removed the furniture, filtered the dust, sealed the room, and pumped out almost all the air, you would not reach true nothingness. A laboratory vacuum is not ordinary emptiness. It is an extreme condition created by careful equipment. But even there, in the best vacuum humans can make, there are usually a few remaining particles, radiation, fields, and the deeper structure of quantum reality. Modern physics suggests that what we casually call empty space is not a dead void. It has physical properties. Quantum fields still exist, and under certain conditions, effects like the Casimir effect show that the vacuum is not the same as absolute nothing. This does not mean empty space is full of usable free energy or fantasy power. It means nothing is much harder to find than common sense assumes. Nature does not give us a simple blank page. Even the blankness has rules, and maybe that is the most important lesson hidden inside an empty room. Your senses evolved to notice big changes: a moving animal, a falling object, a voice, a flame, a face, a threat, a door opening. They did not evolve to reveal every molecule, every microbe, every infrared glow, every drifting fiber, every faint signal, every quantum field. So the brain simplifies. It says empty because empty is useful. It says quiet because the deeper noise is too small. It says still because the motion is too tiny or too balanced to matter for survival. But once you understand what is really there, a silent room becomes something else. It becomes a layered physical environment, a soft cloud of chemistry, motion, memory, energy, and hidden life. You begin to realize that emptiness is often not a fact, but a scale problem. Look too broadly, and the room is vacant. Look more closely, and it becomes crowded beyond imagination. So the next time you stand in a quiet room and feel that nothing is happening, pause before believing that feeling completely. The air is moving, dust is drifting, surfaces are breathing out traces of their materials. Heat is passing between walls and objects, invisible signals are crossing the space. Molecules are carrying old smells into new moments, and beneath all of it, the universe is reminding you that nothingness is rare, maybe even impossible in the way we imagine it. The room was never truly empty. It was only waiting for you to learn how much your eyes leave out. Why everyday matter is mostly empty space. The chair beneath you feels solid enough to trust, yet if your eyes could shrink past the surface, past the fibers, past the molecules, down into the hidden architecture of atoms, you would discover something almost impossible to accept. The matter holding you up is mostly open space, not empty in the simple sense of a blank room, and not meaningless nothing, but vast internal distance between tiny centers of mass and the hazy regions where electrons are likely to be found. Everyday objects feel continuous because your senses are built for the human scale, where wood, metal, skin, glass, and stone behave like firm surfaces. But at the atomic scale, solidity becomes stranger. An atom is not a miniature solar system with little balls calmly orbiting a central sun. That old picture helps beginners imagine scale, but real atoms are more subtle. At the center is a nucleus, incredibly small and dense, containing almost all of the atom's mass. Around it is an electron cloud, not a hard shell, not a spinning bead path, but a spread out region of possibility where electrons exist according to quantum rules. If an atom were expanded until its nucleus were the size of a tiny grain, the outer region of the atom would stretch across a much larger distance, leaving an astonishing amount of space between the dense center and the edge of its influence. And yet your hand does not pass through a table, your bones do not collapse into the floor, and a stone does not behave like fog. The reason is that matter's emptiness is not weakness, it is structured emptiness. Electrons are not tiny, loose decorations floating around a nucleus. Their behavior creates stable patterns, and atoms resist being squeezed into the same space because of the rules governing electrons and the electromagnetic force. When two objects meet, the atoms at their surfaces do not need to be packed solid like bricks to push back. Their electron clouds interact, resist, and prevent ordinary matter from simply flowing through itself. So the solidity you feel is not proof that matter is filled all the way through. It is proof that invisible rules are strong enough to make space behave like substance. This is one of the most beautiful reversals in physics. The world feels solid not because it is full, but because its emptiness is organized. The story became harder to ignore in the early 20th century. when experiments revealed that atoms could not be solid little spheres. In Ernest Rutherford's famous gold foil experiment, tiny particles were fired at a thin sheet of gold. If atoms were like dense pudding all the way through, the particles would mostly slow or scatter gently, but most passed straight through, while a few bounced back sharply. The result was shocking because it suggested that most of the atom was open region, with a tiny dense nucleus at the center, capable of strongly deflecting particles that came very close. It was as if someone fired pebbles at a wall, and nearly all of them passed through, except a few that hit hidden steel points. Matter, which had seemed continuous and thick, was suddenly revealed as mostly spacious at its deepest ordinary level. This does not mean you are made of nothing, and it does not mean matter is fake. That is the wrong lesson. The better lesson is that reality does not need to match the way it feels. Your body has weight because atoms have mass. Your skin has boundaries because atoms interact. A mountain is hard because its atoms are locked into stable arrangements. A diamond is strong because carbon atoms form a tight crystal structure. Water flows because its molecules can slide past each other. Air feels thin because its molecules are spread far apart. The difference between a wall, a river, and a cloud is not that one is real and the other's less real, but that their atoms and molecules are arranged, bonded, and moving in different ways. The emptiness inside matter does not erase its behavior. It makes that behavior possible. Think of a song. Most of the song is not continuous sound. It is shaped by gaps, timing, pauses, and patterns. Remove the spaces, and the music becomes noise. In a similar way, matter is not just stuff packed into stuff. It is pattern, distance, force, and relationship. The spaces inside atoms are not useless gaps. They are part of the structure that allows chemistry to exist. If atoms had no internal spaciousness, there would be no flexible electron clouds, no bonding the way we know it, no molecules folding into proteins, no DNA carrying instructions, no water with its strange life-supporting properties, no light interacting with matter in the rich ways that produce color and transparency. The openness inside matter is not a flaw in creation. It is the stage on which form becomes possible. And this is where the idea begins to feel personal. You look at your hand and see something continuous, familiar, undeniable. But your hand is a living arrangement of atoms, and those atoms are mostly space-shaped by forces. The same is true of your face in a mirror. The walls around you, the ground beneath you, the cup you lift, the page you touch, the planet under your feet. The world is not less real because it is mostly space. It is more mysterious because space, when organized by laws, can become skin, stone, blood, forests, oceans, and eyes that wonder about themselves. What you call solidity is a translation your nervous system gives you, so you can move through life without being overwhelmed by the deeper truth. You are not meant to feel the atomic emptiness of your own body every time you stand up. You are meant to trust the floor. But once you know, even ordinary things become quietly strange. A closed door becomes a pattern of forces. A hand on a table becomes two clouds of matter refusing to merge. A human body becomes a temporary architecture of space and energy, stable enough to breathe, fragile enough to change, and aware enough to ask what it is made of. So the next time something feels absolutely solid, do not dismiss that feeling, but look beneath it in your imagination. Beneath the surface is not a simple block of substance, but a hidden spaciousness held in form by invisible rules. The universe has built the feeling of solidity out of distance. It has made presence from emptiness, and somehow, from atoms that are mostly open space, it has made you. A thinking pattern in the quiet gaps, solid enough to touch the world, and spacious enough to wonder why touch exists at all. How light pushes objects without touching them. A beam of light looks weightless because it arrives without hands, without wind, without any visible body behind it. Yet under the right conditions, it can push matter so gently and so persistently that an object can begin to move. This sounds strange because, in daily life, pushing usually means contact. A hand pushes a door, air pushes a leaf, water pushes a boat. But light belongs to a quieter category of influence. It can transfer momentum even though it has no rest mass, because light carries energy, and in physics, energy can press, nudge, and deliver motion when it is absorbed or reflected. You do not feel sunlight shove your body backward because the pressure is incredibly small, far weaker than the forces you normally notice. But small does not mean imaginary. If light strikes a surface and is absorbed, it gives a tiny push. If it reflects, the push can be a little stronger because the light changes direction. And changing direction means momentum has been exchanged. At human scale, this effect is almost invisible. A lamp does not blow papers off a desk. A flashlight does not knock dust from a shelf. But in space, where there is almost no air resistance and nothing constantly slowing things down, even a tiny steady push can matter. This is the idea behind solar sails. A spacecraft with a very wide, very thin reflective sail can use sunlight not like fuel, but like a continuous pressure. Each photon gives only an almost unimaginably small nudge, but the nudges keep coming. Over time, they can change the craft's motion. It is not fast in the dramatic rocket sense at first, but it is elegant. Motion from light itself, acceleration from a star. The same principle helps shape parts of the natural universe. Around comets, sunlight can push fine dust away from the sun, helping create a dust tail that spreads into space. The solar wind also plays a role in comet tails, especially the ion tail. So it is not only light doing the work, but radiation pressure from sunlight is real enough to help sculpt what we see. Even tiny particles floating in space can be slowly moved by light, and over long times that influence can change orbits, clear dust, or reshape delicate cosmic environments. This is one of the hidden lessons of physics. Forces do not need to be strong to be important. They only need time, direction, and a place where nothing cancels them too quickly. In laboratories, scientists can make light's touch much more precise. A tightly focused laser beam can trap and move microscopic particles, almost like invisible tweezers made of brightness. This works because the electric field of the light interacts with tiny objects and pulls them toward regions where the beam is most intense, while the light's momentum also pushes along the beam's direction. With careful control, researchers can hold tiny beads, study cells, move small biological structures, and measure forces so delicate that ordinary tools would be far too clumsy. Light becomes a hand, not a warm hand, not a solid hand, but a mathematical hand made of direction, energy, and focus. It can hold something without gripping it. It can move something without a finger. And this changes how you think about what touch means. Maybe touch is not always skin against surface. Maybe touch is any transfer of influence, any moment where one part of the universe changes the motion or state of another. There is also a famous object people often misunderstand. The little glass radiometer with black and silver veins that spins when sunlight hits it. It looks like proof that light pressure is turning the blades. But in most ordinary radiometers, the spinning is mainly caused by heating effects in the thin gas inside the bulb, not direct light pressure alone. The black sides get warmer than the shiny sides, and interactions with the remaining gas molecules help drive the motion. This is important because real science is more interesting when we do not turn every beautiful thing into the wrong explanation. Light pressure exists, but not every spinning object in light is spinning for that reason. Truth does not weaken the wonder, it sharpens it. The real wonder is that light can push even when the push is too faint for our senses, and that the universe is full of effects too subtle for daily life, but powerful when conditions change. On Earth, air, friction, weight, and rough surfaces overwhelm light's pressure. In space, on microscopic scales, or inside precise experiments, the hidden push becomes visible. And once you know this, sunlight itself begins to feel different. It is not just illumination. It is not only warmth, color, or the signal that morning has arrived. It is also a stream of momentum flowing outward from the sun, touching planets, dust, sails, and surfaces with a patience no human hand could match. Every bright room, every sunlit window, every reflection on water carries a force so gentle it seems almost like nothing. But nature often builds great changes from almost nothing repeated long enough. A photon does not need to shout to be real. A beam does not need to feel heavy to carry motion. And perhaps that is the quiet lesson hidden in light's push. Influence is not always dramatic. Contact is not always visible. And some of the most persistent forces in existence arrive so softly that the world moves before we ever realize it has been touched. The strange physics hiding in everyday shadows. A shadow is not a piece of darkness lying on the ground. It is a silent map of where light was interrupted. A shape made not from something added to the world, but from something that failed to arrive. That is why shadows feel so familiar and yet so strange. You see one beneath your hand, your chair, a tree, a building, and your mind treats it as a simple dark patch. But a shadow is actually a record of geometry, distance, surface, atmosphere, and the size of the light source itself. It is physics drawn in grey. The simplest idea is this. Light usually travels in straight lines through air, and when an object blocks some of those paths, the area behind it receives less light. But the moment you look more carefully, the simplicity begins to dissolve. A shadow is rarely just one clean black shape. It often has a darker center and a softer edge. The darker center is called the umbra, the region where most direct light is blocked. Around it is the penumbra, where only part of the light source is blocked, so the shadow fades gradually instead of ending like a cut line. This happens because most light sources are not perfect points. The sun may look small in the sky, but it still has a visible width, and light reaches you from different parts of its disk. A lamp, a window, a candle flame, a phone flashlight each has size, shape, and direction. Because of that, the shadow's edge becomes a negotiation, not a border. Stand close to a wall with your hand between the wall and a lamp, and the shadow looks sharper. Move your hand farther away, and the edge spreads and softens. Nothing magical happened to your hand. What changed was the geometry of light. The shadow became wider, blurrier, less certain, because light from different parts of the source could sneak around different edges. In this way, shadows quietly teach you that seeing is not only about objects, but about relationships. Where the light is, where the object is, where the surface is, and how far apart everything sits. Shadows also reveal that darkness is not always black. On a sunny day, the shadow of a tree or a person may look blue-grey rather than pure dark, especially on snow or pale concrete. This is because direct yellowish sunlight is blocked, but scattered skylight still reaches the shadow. The blue of the sky is not just a colour above you. It can become the light inside a shadow, so a shadow outdoors is often filled with the sky. It is not the absence of all light, but the absence of direct sunlight mixed with the presence of indirect light. This is why shadows indoors can look warm or cool depending on the surrounding walls, curtains, lamps, and reflected surfaces. A white wall can bounce light into a shadow and lift it. A red surface nearby can tint it. A cloudy sky can erase hard shadows almost completely because clouds spread sunlight into many directions, turning the whole sky into a giant soft lamp. On those days, objects still block light, but the light arrives from so many angles that shadows lose their sharp identity. The world looks flatter, softer, quieter, because the shadows are no longer strong enough to carve depth into everything. This is one reason artists study shadows so carefully. Shadows do not merely darken a scene. They give objects weight, position, roundness, and mood. Without shadows, a face can look artificial, a room can look unreal, and a landscape can lose its shape. Your brain uses shadows as clues. It reads them to estimate where things are, how tall they might be, whether a surface is curved or flat, whether something is floating or touching the ground. In fact, small contact shadows, the tiny dark areas where objects meet surfaces, are one of the reasons the world feels grounded. Remove them in a digital image, and an object may appear to hover unnaturally. Your brain may not know the physics consciously, but it feels the mistake. Shadows are part of how reality convinces you it has depth. There is an even stranger detail hiding at the edges. Light can bend slightly around obstacles, a behavior called diffraction. In everyday shadows, this effect is usually subtle, because most objects are large compared with the wavelength of visible light. But under the right conditions, especially with very small gaps, thin edges, or carefully controlled light, shadows are not perfectly sharp because light behaves like a wave as well as a stream of particles. The edge of a shadow can contain faint fringes, delicate patterns of brightness and darkness created by interference. It is as if light, when blocked, still whispers around the obstacle. You normally do not see this in the shadow of a chair or a tree, because ordinary light is mixed from many wavelengths and directions, and the patterns blur away. But the principle is real, and it reminds you that even a shadow, the thing we treat as simple darkness, contains evidence of the wave nature of light. Shadows have also helped humans measure the world. Long before modern instruments, people used shadows to tell time, track seasons, estimate direction, and understand Earth's shape. A sundial is not just an old clock. It is a machine that uses the planet's rotation to move a shadow. The changing length of your shadow across the day is a visible sign of Earth turning under sunlight. At noon, when the sun is high, your shadow becomes shorter. Near sunrise or sunset, it stretches long across the ground because the sunlight arrives at a low angle. The same principle becomes enormous during an eclipse. When the moon passes between Earth and the sun, its shadow falls onto our planet, and anyone standing inside the darkest part sees the sun covered. A solar eclipse is not an omen or a tear in reality. It is shadow geometry on a cosmic scale. The same principle as your hand blocking a lamp, but expanded until the objects are worlds. And perhaps that is what makes shadows so quietly powerful. They connect the smallest daily experience with the motion of planets. The shadow under your cup and the shadow of the moon across Earth belong to the same family of events. One is domestic, one is celestial, but both are written by light meeting an obstacle. So the next time you see a shadow on the floor, do not think of it as nothing. It is not just darkness, it is information. It tells you where light came from, what blocked it, how large the source was, how far the object stood, what color the surrounding light carried, how the surface received it, and how your brain turns contrast into depth. A shadow is the world's quiet negative image, a shape made by absence but filled with evidence. It is what remains when light is denied a path, and in that denial, the hidden structure of the scene becomes visible. Even darkness, when you look closely enough, is teaching you how light behaves. The hidden geometry, inside smoke, clouds, and blood. Smoke does not wander randomly. Clouds do not bloom without structure. And blood does not move through you like red water in simple tubes. All three are drawing hidden geometries in motion, using curves, branches, spirals, sheets, and tiny repeating patterns that appear chaotic only because your eyes cannot slow them down enough to read them. Watch smoke rise from a candle, and at first it may look like a smooth, thin column, almost like a grey thread being pulled upward by an invisible hand. That early smoothness happens because the warm smoke is lighter than the cooler air around it, so it rises in a fairly organized stream. But as it climbs, the stream becomes unstable. The air around it pulls, mixes, folds, and disturbs it. The clean column begins to curl. Small waves appear along its sides. Those waves roll into loops. The loops stretch into twisting shapes. And suddenly the smoke becomes a living sculpture of turbulence. It looks messy, but it is not meaningless. It is the geometry of fluids trying to mix. Smoke reveals what air normally hides. The fact that air is never just there, but always capable of rolling, folding, and forming invisible rivers. The smoke particles do not create the motion by themselves, they make the motion visible. They are like ink dropped into moving water, showing you the path of something you could not see before. This is why smoke can look like silk one moment and a storm the next. It is crossing a threshold from smooth flow to turbulent flow, from simple order into layered complexity. And once you recognize that, you start seeing the same hidden language in clouds. A cloud may look soft, like a floating object with edges, but it is not an object in the ordinary sense. It is a changing population of tiny water droplets or ice crystals suspended in air. constantly forming, evaporating, merging, and reshaping. Its edges are not walls. They are zones of negotiation, places where moist air, temperature, wind, and pressure conditions decide whether vapor remains invisible or becomes visible as droplets. This is why clouds can have sharp-looking towers, feathered streaks, cauliflower domes, flat bases, rippled layers, or wave-like curls. A cumulus cloud rises when warm, moist air lifts and cools, allowing water vapor to condense. Its rounded towers often show upward motion, like invisible columns of air pushing into the sky. Thin, high clouds can stretch into delicate fibers because ice crystals are being spread by fast winds above. Sometimes clouds form repeating rolls or waves because air layers slide past one another, creating patterns that resemble the surface of water disturbed by wind. The sky is not painting clouds casually. It is revealing the geometry of moving air. Every cloud is a temporary diagram of atmospheric conditions, a visible answer to questions you did not know the air was asking. Where is it rising? Where is it cooling? Where is it mixing? Where is it stable? Where is it about to change? Even the familiar branching shapes in storm clouds or the spreading anvil at the top of a thunderstorm come from physical limits and flows, not artistic chance. A thunderstorm grows upward until it reaches air that resists further rise, then spreads sideways, like a fountain hitting a ceiling. What looks like drama is often geometry under constraint, and then, strangely, the same kind of hidden pattern appears inside your own body. Blood does not travel through one simple pipe. It moves through an enormous branching network, arteries dividing into smaller arteries, then arterioles, then capillaries so narrow that red blood cells often pass through one by one, then venules and veins carrying blood back again. This branching is not decorative. It solves a problem. Every living cell needs oxygen, nutrients, and waste removal. But the body cannot give each cell its own separate highway from the heart. So the circulatory system branches, again and again, reaching deep into tissues with increasing delicacy. The large vessels are like highways, the smaller vessels like streets, and the capillaries like narrow footpaths, reaching individual neighborhoods of cells. This branching pattern increases reach while saving space and energy. It is not perfectly symmetrical because the body is not a machine drawn with a ruler. It grows, adapts, repairs, and responds to need. Muscles that work hard can develop richer blood supply. Wounds call for new vessel growth. Organs have different flow demands. The geometry of blood is therefore not only a structure, it is a history of function. Even within the vessels, blood itself is not a simple liquid. It is a suspension full of red blood cells, white blood cells, platelets, proteins, and plasma. Red blood cells are flexible, shaped like soft discs with dimples, built to squeeze through tight capillaries and maximize surface area for gas exchange. In larger vessels, blood may flow in smooth layers, with cells tending to move differently near the center than near the vessel walls. In tiny vessels, the behavior becomes even stranger because individual cells matter. The flow is shaped not only by the tube, but by the bodies moving through it. Your pulse, then, is not just a beat. It is a traveling wave through a branching living geometry. The heart does not simply pour blood forward like a bucket. It sends rhythmic pressure waves through elastic vessels that expand and recoil. Your arteries are not stiff pipes. They are responsive tissues, storing and releasing energy with each heartbeat. This is why blood flow is both mechanical and biological, both engineered by physics and softened by life. Smoke, clouds, and blood seem unrelated at first. One rises from fire, one floats in the sky, one circulates inside the body. But all three show how nature builds form from movement. Smoke reveals turbulence. Clouds reveal atmospheric structure. Blood reveals branching transport and living flow. Each one is a visible or hidden geometry created by motion under rules. And this matters because it changes the way you look at disorder. What appears random may be patterned at another scale. What appears soft may be shaped by strict conditions. What appears formless may be a temporary solution to a physical problem. A curl of smoke, a cloud tower, and a capillary bed are not the same thing, but they all whisper the same lesson. The world often draws before it explains. It draws with air, with vapor, with cells, with heat, with motion, with need. And perhaps your own life is like that too. Less like a straight line and more like a branching flow, shaped by obstacles, openings, pressure, and time. The next time you see smoke twisting upward, or clouds slowly changing shape, or the faint blue-green trace of a vein beneath your skin, remember that you are looking at geometry in motion. Not cold geometry locked on a page, but living geometry, temporary geometry, geometry that breathes, rises, circulates, and vanishes. The hidden order was never absent. It was simply moving too gently, too deeply, or too beautifully for you to notice at first glance. The hidden physics of lightning paths. Lightning does not fall from the sky as a single finished spear. It searches, hesitates, branches, and builds its path in fragments before your eyes ever see the flash. From the ground, a lightning bolt looks instant, as if the cloud simply throws fire downward in one violent decision. But the real process is far more delicate and strange. Inside a thunderstorm, countless collisions between ice crystals, water droplets, and soft hail called graupel help separate electric charge. The exact details can be complex, but the basic result is that different parts of the cloud become electrically different from each other, and the ground beneath the storm can be influenced as well. The storm becomes a huge natural battery, with invisible tension growing between regions of opposite charge. At first the air resists. Air is normally an insulator, meaning it does not easily allow electric current to pass. But as the electric field strengthens, the air begins to fail. It does not fail everywhere at once. It breaks in steps. A faint, invisible to the eye channel called a stepped leader moves downward from the cloud in short jumps, pausing and splitting, testing possible routes through the air. This is one of the most important hidden truths about lightning. The path is not drawn after the flash. The path is prepared before the brightness you notice. The leader branches because the air is not perfectly uniform. Temperature, humidity, dust, rain, pressure, charge particles, and the changing electric field all affect which direction becomes easier for the next step. People often say lightning takes the path of least resistance, but that phrase can be misleading if it makes you imagine one clean road already waiting. The path is more like a negotiation created moment by moment. Many possible channels begin. Most fail, a few extend farther. The bolt is not choosing like a mind. It is following physical conditions that change as the channel grows. Meanwhile, objects on the ground respond before the main flash arrives. Trees, buildings, towers, hills, and even smaller pointed objects can send upward streamers, rising filaments of charge reaching toward the descending leader. When one of these streamers connects with the leader from above, the channel is completed. Then the brilliant return stroke races upward from ground to cloud along the prepared path, carrying a powerful electric current and producing the flash you see. The part that looks like lightning coming down is often followed by the brightest visible surge moving upward through the channel. Your eye compresses the whole event into one dramatic moment, but the storm has been quietly constructing the route in the darkness just before it. This is why lightning branches. It is not a decorative shape. It is a record of failed possibilities. Every fork is a path the electric field began to explore. Every jagged turn shows how the channel responded to tiny differences in the air. Lightning looks wild because the air itself is a complex landscape. There are no visible roads in the sky, but electrically, some regions become easier to break through than others. When the current finally flows, the air inside the channel becomes plasma, a hot, electrically conducting state where atoms are stripped of some electrons. The temperature in that narrow channel can rise to around tens of thousands of degrees, much hotter than the surface of the sun, but only for a very short time and in a very thin path. This sudden heating makes the air expand explosively, and that rapid expansion creates thunder. Thunder is not a separate phenomenon added afterward. It is the sound of air reacting to the lightning's heat. The flash and the sound are born from the same event, but light reaches you much faster than sound. so the sky lets you see the violence before you hear it. Even the distance between flash and thunder becomes a simple way to estimate how far away the strike occurred, because sound takes time to travel through air. Lightning also does not always strike the ground. Much of it happens inside clouds, or between clouds, lighting up the storm from within, like a nervous system firing across a dark brain. Some lightning spreads horizontally across enormous distances. Some appears as sheet lightning when the bolt is hidden, but the cloud glows. Some rare electrical events reach upward above storms, producing strange high-altitude flashes such as sprites, which are real but usually difficult to see without special conditions and equipment. All of this shows that lightning is not merely a bright line. It is an electrical conversation between cloud, air, ground, and atmosphere. It reveals how nature handles imbalance. A storm separates charge, tension grows, air resists, invisible channels form, connection happens, energy rushes through, and the sky briefly writes its solution in light. And perhaps that is why lightning feels so ancient to us. It is not only dangerous, it is meaningful to the eye because it makes the invisible visible. For one fraction of a second, you see an electric field made bright. You see air becoming a conductor. You see a path created out of tension. You see branching decisions that were never conscious, yet somehow look almost alive. The next time lightning cuts across the sky, do not think of it as a simple bolt thrown downward. Think of it as a hidden map, suddenly illuminated. A map of charge, resistance, failed routes, successful connection, and energy-finding release. The flash is not the beginning of the story. It is the moment the story becomes visible. How sound can shape sand and water. A sound is not just something you hear. Under the right conditions, it becomes a sculptor, a set of invisible hands that can gather sand into patterns, wrinkle water into living geometry, and reveal that vibration has a shape long before it becomes music in your mind. Most of the time, sound seems temporary. A word is spoken and disappears. A note is played and fades. A door closes, a glass rings, a phone hums, and then the room returns to quiet. But the sound did not simply vanish like a thought. It moved through matter as vibration, compressing and relaxing air, shaking surfaces, passing energy from one place to another. And when that vibration meets the right material in the right way, it can leave a visible trace. This is the hidden beauty behind the old Chladni plate experiment, one of the simplest and most haunting demonstrations in physics. Imagine a thin metal plate sprinkled with fine sand. At first, the grains lie scattered without meaning. Then the plate is vibrated at a certain tone, and suddenly the sand begins to move. It jumps, slides, escapes from some regions, and gathers in others. Within seconds, what looked random becomes a pattern. Lines, curves, stars, webs, shapes that seem almost designed. But nothing mystical has been added. The plate is forming a standing wave. Some parts of the metal are moving strongly up and down, while other parts remain almost still. The still regions are called nodes, and because the sand is shaken away from the active areas, it settles along those calmer lines. In other words, the sound does not draw the pattern directly like a pencil. It shakes the world until the quieter places reveal themselves. Change the tone and the pattern changes. A lower frequency may produce a simpler shape. A higher one may create more detailed divisions. The plate is not responding to sound as a passive object. It is answering with its own structure, its own size, thickness, stiffness, and boundaries. The same note on a different plate may create a different design because every object has its own way of vibrating. This is why a guitar string, a drum head, a wine glass, a metal bowl, and a wooden table all produce different sounds when struck. They each have natural modes of vibration, preferred patterns of motion, like hidden signatures inside the material. Sound reveals those signatures. It makes the invisible architecture of vibration visible. And once you understand that, the sand patterns stop looking like magic and start looking like a language spoken by matter when energy moves through it. Water gives an even softer, stranger version of the same lesson. Place water on a vibrating surface, or send sound into it carefully, and the surface can form ripples, rings, standing waves, and even organize patterns that shift as the frequency changes. Water is especially expressive because its surface is flexible, constantly pulled by gravity, surface tension, and motion. When vibration passes through it, some waves travel outward, some reflect back, and under the right timing, they overlap in stable patterns. These are not permanent sculptures. They are temporary agreements between motion and resistance. The water keeps moving, yet the pattern can appear to hold still because the waves are repeating in a steady rhythm. This is similar to how a jump rope can form a stable loop when moved at just the right pace, even though every part of the rope is still in motion. With water, the result can look alive. Tiny peaks rising and falling, circles breathing outward, grids appearing and dissolving, droplets jumping when the vibration becomes strong enough. Scientists study these patterns not because they are pretty, although they are, but because they reveal how fluids respond to periodic forcing. One famous example is called Faraday waves, named after Michael Faraday, who studied how vibrating a container of liquid could create standing wave patterns on the surface. These waves can form stripes, squares, hexagons, and more complex arrangements depending on the vibration and the liquid. Again, the important truth is not that sound commands water in a supernatural way. It is that vibration transfers energy, and matter organizes that energy according to real physical rules. This distinction matters because videos of cymatics, the study and display of visible sound patterns, are sometimes wrapped in exaggerated claims, as if every shape proves hidden cosmic messages or secret healing codes. The real science is already fascinating enough without pretending. Sound can shape sand and water because vibration creates zones of motion and stillness, pressure and release, reinforcement and cancellation. When waves meet, they can add together and become stronger, or they can partly cancel and become weaker. That simple behavior can generate astonishing complexity. It explains why some sounds resonate in a room while others fade, why a singer can make a glass tremble if the pitch matches the glass's natural vibration closely enough, and why engineers must pay attention to vibration in bridges, engines, aircraft, buildings, and machines. Resonance is powerful because a small repeated push, timed correctly, can build into a large response. This is why sound shaping matter is not just a classroom curiosity. It belongs to a wider world of physics where rhythm matters. In technology, sound waves can be used to move tiny particles, sort cells, clean surfaces, image the inside of the body with ultrasound, and even hold small objects in place using acoustic levitation under carefully controlled conditions. In those cases, sound becomes a tool, not just a sensation. It can push and arrange matter because pressure waves carry energy and momentum through a medium. But the medium matters. Sound needs something to travel through, like air, water, metal, or tissue. In empty space, where there is no material to compress and relax, ordinary sound cannot travel. That alone makes sound different from light. Light can cross the vacuum between stars, but sound is more intimate. It needs matter. It needs contact from particle to particle. It is the universe whispering through materials, not across nothingness. And perhaps that is why visible sound patterns feel so moving. They show you that what you hear is only one version of vibration. Your ear turns vibration into experience, but sand turns it into lines. Water turns it into ripples, a drum turns it into rhythm, a violin turns it into tone. Your chest may feel deep bass as pressure, while a glass may answer a pitch with trembling. The same physical event can become music, movement, pattern, or stress, depending on what receives it. The world is not divided neatly between sound and shape. Shape can hide inside sound, waiting for the right surface to expose it. And when you watch sand gather into elegant lines, or water rise into patterned motion, you are seeing a quiet truth about reality. Form does not always come from solid things being carved. Sometimes form comes from motion repeating itself. Sometimes a pattern is not built by adding material, but by shaking a system until order emerges from the places that move least. This is why the experiment feels almost philosophical. The sand does not choose beauty. The water does not understand symmetry. The plate does not intend to draw. Yet when energy, timing, and structure meet, beauty appears anyway. Nature does not need intention to create order. It only needs rules, movement, and enough time for hidden relationships to become visible. So the next time you hear a tone, a hum, a song, or a low vibration passing through a wall, remember that sound is not merely disappearing into the air. It is touching matter in small ways, testing surfaces, waking hidden modes, carrying pressure through the world. Most of the time, the patterns remain invisible because nothing has been sprinkled on the plate. No water surface has been prepared. No experiment has slowed the moment down for your eyes. But the shaping is real. Somewhere inside the vibration, there is geometry waiting to be seen. And in that quiet realization, sound becomes more than noise, more than music, more than a signal. It becomes a reminder that the invisible can still have form, and that even the briefest note may leave the world slightly rearranged before it fades. Why magnets reveal invisible field lines. A magnet looks like a simple object until it makes invisible space behave as if it has a hidden shape. Place a bar magnet under a sheet of paper, sprinkle iron filings above it, and something almost eerie happens. The filings stop looking like dust and begin arranging themselves into graceful curves, looping from one end of the magnet to the other, thicker near the poles, softer farther away, as if the magnet has drawn a secret map through the air. But the lines you see are not strings, not wires, not little roads physically floating around the magnet. They are a visible translation of something deeper, a magnetic field, an invisible region of influence surrounding the magnet, shaping how certain materials respond inside it. The iron filings reveal the field because each tiny piece of iron becomes temporarily magnetized. In the presence of the magnet, the filings act like miniature compass needles, turning until they align with the local direction of the magnetic field. They also attract one another end to end, forming chains that trace the field's pattern. What looks like a drawing made by the magnet is really matter aligning itself with an unseen order. The filings are not creating the field. They are showing you where the field already was. This is the quiet power of the experiment. It turns invisible influence into visible structure. Magnetic field lines are a human-made way of representing direction and strength. Where the lines appear crowded together, the field is stronger. Where they spread apart, the field is weaker. Around a simple bar magnet, the pattern emerges because one end behaves like a north pole and the other like a south pole. Outside the magnet, the field is usually described as looping from north to south, while inside the magnet, the field continues the loop back again. This looping matters because magnetic fields do not simply begin at one point and vanish at another in the way a road begins and ends. In ordinary magnets, north and south poles come as pairs. If you cut a bar magnet in half, you do not get an isolated north pole and an isolated south pole. You get two smaller magnets, each with its own north and south. Cut them again, and the pairing remains. This tells you something profound about magnetism. It is not built from loose magnetic charges sitting separately, at least not in everyday experience. It is built from alignment, circulation, and paired structure. Deep inside magnetic materials, many atoms act as tiny magnetic sources because of the behavior of electrons, including their spin and motion. In most materials, these tiny magnetic effects point in random directions and cancel out, leaving no large magnetism you can notice. But in materials like iron, nickel, and cobalt, groups of atoms can form regions called magnetic domains, where many microscopic magnetic directions line up together. In an unmagnetized piece of iron, different domains may point in different directions, cancelling one another overall. But when the domains become aligned, the material becomes a magnet. A magnet, then, is not magic trapped in metal. It is a piece of matter where countless microscopic magnetic tendencies have found a shared direction. That shared direction extends outward as a field, and the field can reach across empty-looking space. This is why a magnet can pull a paperclip without touching it. Nothing visible crosses the gap, but the magnetic field is there, and the iron in the paperclip responds. The paperclip becomes temporarily magnetized, Its domains shift slightly, and it is drawn toward the stronger part of the field. In that moment, the empty space between magnet and metal is not empty in the practical sense. It contains a pattern of influence strong enough to move matter. A compass works by the same principle, but more delicately. Its needle is a small magnet free to turn. Earth itself has a magnetic field, generated largely by motion in its liquid outer core, where electrically conducting molten iron alloys move in complex flows. The compass needle aligns with this planetary field, giving humans a way to navigate long before satellites and maps in pockets. What feels like a tiny needle finding north is actually a small magnet responding to a field that surrounds the entire planet. Earth's magnetic field is not perfectly simple, and magnetic north is not exactly the same as geographic north. But the basic idea remains astonishing. A needle on your palm can answer a motion deep inside Earth. Magnets reveal field lines, because they make you realize that space is not only a stage where objects sit. Space can carry fields. A field is a way of saying that every point around an object has a condition, a direction, a possibility for force if the right kind of material or moving charge enters it. You do not need to see the field for it to be real. You know it by what it does. The iron filings curve, the compass turns, the paperclip jumps, the motor spins, the speaker vibrates. Magnetic fields are central to electric motors and generators, where magnetism and electricity work together to turn motion into electrical energy or electrical energy into motion. In a speaker, changing electric current creates changing magnetic effects that move a coil and push a cone, producing sound waves. In a generator, moving magnets and coils help produce electricity. The quiet curves around a classroom magnet are connected to the machinery of modern life. But it is important to keep the wonder honest. The field lines you see in drawings are not actual lines etched into space. They are like contour lines on a map, useful symbols that help you understand shape and strength. The real magnetic field is continuous, not made of separate threads. The filings gather into lines because they interact with each other as well as the field. So the pattern is a visual clue, not a perfect photograph of the field itself. Science often works this way. It gives you instruments that do not show reality directly, but translate it into something your senses can handle. A thermometer translates molecular motion into a number. A camera translates light into an image. Iron filings translate magnetic influence into pattern. And once you see those patterns, the world changes slightly. A refrigerator magnet, a compass, an electric motor, a credit card strip, a magnetic resonance scanner, the field around Earth, all become part of the same hidden language. Magnetism teaches you that influence does not always announce itself with contact. It can curve through space, organize matter, guide needles, store information, and protect planets from some charged particles from the sun. It is silent, but not passive, invisible, but not absent. The filings on paper are only the moment when the unseen becomes visible enough for the human mind to believe it. So the next time you hold a magnet and feel it tug at metal, pause before calling it simple. Around that small object, space has direction. Inside that metal, countless tiny alignments are acting together. Between the magnet and the paperclip, there is no hand, no string, no wind, no visible bridge, and still something reaches. The field lines are not the reality itself. They are the shadow of a deeper order. And maybe that is why magnets feel so strangely satisfying to watch. They remind you that the world is filled with patterns your eyes cannot see. And sometimes all it takes is a little iron dust to prove that the invisible has been shaping the visible all along. How vortices appear in water, air, and space. A vortex begins the moment motion stops moving straight and starts remembering how to turn. You have seen it in a sink as water twists toward a drain, in a curl of wind lifting leaves from the street, in the spiral arm of a distant galaxy, and perhaps in the small whirl that forms when you stir tea and watch the surface dip at the center as if the liquid has opened a quiet eye. At first, a vortex looks like a simple swirl, but it is really one of nature's favorite ways of organizing motion when a fluid or a cloud of matter has rotation, flow, and a path to follow. In water, a vortex can form when liquid begins draining downward and tiny differences in motion become amplified. The water does not need to be told to spin. It may already have slight rotation from how the basin was filled, how your hand moved through it, how the container is shaped, or how the liquid rubs against the surface. As the water moves inward toward the drain, that small rotation can become faster. For the same reason, a spinning ice skater turns more quickly when pulling their arms inward. The moving water is drawn closer to the center, and because its turning motion is conserved in a broad sense, the spin tightens. The center can dip, because pressure is lower there than at the outer regions, so the surface curves downward into a funnel. What you are seeing is not water being mysteriously sucked by a hole, but water balancing gravity, pressure, rotation, and friction in real time. The vortex is a compromise between falling inward and turning around. This is why not every draining sink forms a dramatic whirlpool. The size of the container, speed of draining, shape of the basin, roughness of the surface, and existing motion in the water all matter. The old idea that water always drains one way in one hemisphere and the opposite way in the other is misleading for sinks and bathtubs, because local conditions are usually much stronger than Earth's rotation at that small scale. Earth's rotation can shape huge systems like hurricanes and ocean currents, but your bathroom sink is more easily ruled by the last little push the water received. In rivers and oceans, vortices can appear when flowing water meets obstacles, uneven ground, competing currents, or changes in speed. Behind a rock in a stream, you may see little whirlpools forming and shedding one after another, like the water is leaving behind rotating fingerprints. These spinning structures help mix the water, move sediment, carry nutrients, and shape riverbeds over time. In the ocean, eddies can grow enormous, sometimes stretching for many kilometers, transporting heat, salt, and marine life across wide regions. A vortex is not just a pretty spiral. It is a moving engine of mixing. It takes differences, fast and slow, warm and cold, dense and light, and folds them together. Air does something similar, though it often hides the motion unless dust, leaves, clouds, or moisture reveal it. A dust devil forms on hot ground when sun-warmed air rises quickly and begins to rotate. If the rising column tightens, it can pick up dust and become visible. A small spinning tower born from heat, unstable air, and local rotation. A tornado is far more powerful and dangerous, forming under special storm conditions where strong wind shear, rising air, and thunderstorm structure allow rotation to be stretched and intensified. The tornado's visible funnel is not the whole vortex. It is the part where water droplets, dust, and debris make the spinning air visible. The true rotating motion can extend beyond what your eyes can see. Hurricanes are larger still, not simple whirlwinds but massive rotating heat engines fed by warm ocean water, moist rising air, and Earth's rotation. Air near the surface moves inward toward lower pressure, rises, releases heat as water vapor condenses, and helps power the storm. The rotation organizes the system into bands, and an eye, a calm center surrounded by violent motion. The eye of a hurricane can feel almost impossible, a quiet space created by one of Earth's most powerful storms. But that calm is not peace in the emotional sense. It is structure. It is what happens when rotating air, pressure, rising motion, and conservation of angular momentum arrange themselves on a planetary scale. In space, vortices appear in forms that are stranger, but connected by the same basic idea: rotation, organizing matter. A forming star can be surrounded by a rotating disk of gas and dust, because the original cloud that collapsed under gravity usually had some tiny amount of spin. As gravity pulls material inward, the rotation becomes more important, and instead of everything falling straight into the center, much of it spreads into a disk. From such disks, planets can form. Around black holes, gas can also spiral into an accretion disk, heating up as it moves inward and releasing enormous energy before crossing the point beyond which escape becomes impossible. The gas is not falling like a stone dropped into a well. It is orbiting, colliding, heating, losing energy, and slowly spiraling through a rotating structure shaped by gravity. Galaxies, too, often display spiral patterns, though their arms are not simple whirlpools of stars circling like water in a drain. The stars orbit the galactic center, but spiral arms are more like long-lived patterns of density, places where gas, dust, and star formation become more concentrated. Still, rotation is central to their shape. Across all these scales, from a teacup to a thunderstorm to a disk around a newborn star, vortices show how motion can become architecture. They are not objects in the ordinary sense. You cannot pick up a vortex and hold it. It is a pattern maintained by movement. Stop the motion and the vortex disappears. This makes a vortex feel almost alive because its identity depends on flow. It is there, but only while something is happening. It has a center, but the center may be the emptiest part. It has a shape, but the shape is constantly being remade. And perhaps that is why vortices catch the eye so deeply. They show us order without stillness. They reveal that nature does not always build form by stacking solid pieces together. Sometimes it builds form by directing motion around a center. A whirlpool, a dust devil, a hurricane, a rotating disk of gas in space. Each one is a reminder that spirals are not decorations placed on reality, but solutions reality discovers when flow, rotation, gravity, pressure, and time meet. So the next time you watch water circle a drain or leaves twist in a sudden gust, do not dismiss it as a small accident. You are seeing the same physical instinct that helps shape storms, oceans, planets, and cosmic disks. You are watching movement find a center, curve around it, tighten, stretch, and briefly become visible as form. A vortex is the universe drawing a spiral with whatever material it has available. Water, air, dust, cloud, gas, or stars. And then letting it vanish when the motion no longer needs that shape. Why snowflakes never repeat exactly? A snowflake is born as a tiny crystal, but it falls through the sky as a private history of every temperature, every breath of moisture, and every invisible turn it met on the way down. From far away, snow can look simple, like soft white dust gathering on rooftops and branches, but each flake is a record of changing conditions written in ice. It usually begins high in a cold cloud, when water vapor freezes onto a microscopic particle, such as dust, pollen, sea salt, or another tiny speck suspended in the air. That first frozen seed becomes a crystal, and because water molecules arrange themselves in a particular shape when they freeze, the crystal naturally tends towards six-sided symmetry. This is why so many snowflakes have 6 arms or 6 corners. It is not because the sky is decorating them by imagination, but because the molecular structure of ice favors that geometry. Deep inside the ice, water molecules join in an orderly pattern, and that hidden order expands outward into visible form. But the moment the crystal begins to grow, perfect simplicity disappears. A snowflake does not form all at once. It grows as it travels. It moves through layers of air that are slightly warmer, colder, wetter, drier, calmer, or more turbulent, and each layer changes how water vapor attaches to its surface. At one temperature, the crystal may grow flat plates. At another, it may grow long needles. Under different humidity, it may develop branching arms, hollow columns, broad stars, or delicate fern-like patterns. The shape is not random, but it is sensitive. Tiny changes in temperature and moisture can change the growth style. This means a snowflake is not just a frozen drop. In fact, many snowflakes are not frozen raindrops at all. They are crystals grown directly from water vapor in the cloud. A frozen raindrop becomes sleet or grapple-like ice depending on conditions. But the classic snowflake is built molecule by molecule from vapor becoming solid. That slow construction is what allows such intricate shapes to appear. The 6 arms of one snowflake often look similar to each other because they are growing at the same time in the same tiny neighborhood of air. If one arm experiences a certain temperature and humidity, the other arms experience almost the same conditions, so they grow in similar ways. But they are not perfectly identical. One arm may catch slightly more vapor, another may be damaged by a collision. Another may grow a side branch a little sooner. Even within a single flake, symmetry is a tendency, not a guarantee. Now imagine two separate snowflakes trying to become exactly alike. For that to happen, they would need to begin with nearly the same tiny seed, grow at the same rate, pass through the same sequence of temperatures and humidity levels, meet the same air currents, avoid the same collisions, collect the same number of molecules in the same places, and arrive on Earth without any difference in damage or melting. The number of microscopic choices is enormous. This is why people say no two snowflakes are exactly alike. It is not that nature has a rule forbidding repetition. It is that the path to exact repetition is so unbelievably specific that it becomes practically impossible for complex snow crystals. Very simple crystals, especially tiny ones, can look extremely similar, and at a basic level some small ice forms may be hard to distinguish. But the detailed branching snowflakes people imagine when they think of uniqueness are shaped by so many changing conditions that exact duplication is not realistically expected. Each one is like a diary written in temperature and vapor. One flake may pass through a moist layer and grow feathery branches. Another may pass through drier air and remain simpler. One may tumble, break, partially melt, refreeze or collide with other crystals. Some flakes join together into clumps, which is why snowfall often looks fluffy rather than like individual perfect stars. Near the ground, if the air is warmer, snowflakes can become wet and sticky. In colder, drier air, they may stay sharper and powdery. The snow beneath your feet is therefore not one thing, but a collection of weather histories. Every flake is a small archive of the cloud it came from and the journey it survived. And this is where the science becomes quietly beautiful. The snowflake's uniqueness does not come from chaos alone, and it does not come from perfect design. It comes from the meeting of strict rules and changing circumstances. The rule is the structure of ice, the six-sided tendency, the way water molecules prefer to bond. The circumstance is the journey, the shifting sky, the invisible air, the moisture, the temperature, the collisions, the time spent falling. A snowflake is what happens when order travels through variation. That is why it can look both mathematical and fragile, both planned and accidental. It carries symmetry because of molecular law, but it carries individuality because no falling path is repeated exactly. And perhaps that is why snow feels so strangely emotional when you stop to think about it. It covers the world in sameness, turning streets, roofs, trees, and fields into one quiet white surface. Yet that sameness is made from countless tiny differences. From a distance, snow is a blanket. Up close, it is a crowd of unrepeatable structures. The world becomes soft because millions of small unique histories have landed together. There is a lesson hidden there, gentle but difficult to forget. Nature does not need to choose between pattern and individuality. It can make both at once. The same laws can produce endless variety. The same water molecule, following the same basic rules, can become a plate, a star, a needle, a column, a branch, a broken fragment, a glittering crystal on a sleeve. So the next time snow falls, try to imagine the unseen biography inside each flake. The cold cloud where it began, the vapor that fed it, the air that turned it, the temperatures that shaped its arms, the tiny accidents that made it different from every other flake around it. It may melt on your glove in seconds, but before it disappears, it has already carried a whole sky inside its form. A snowflake never repeats exactly because the sky never repeats exactly. Every fall is a new set of conditions, every crystal a brief answer to them, and every melting flake a reminder that even the smallest things can be shaped by a journey no one else has taken. How bubbles solve mathematical problems. A soap bubble does not know mathematics, yet the moment it forms, it begins solving a problem that would take a human mind equations, diagrams, and careful reasoning to describe. You dip a wand into soapy water, lift it into the air, and a thin film stretches across the opening as if it has made a quiet decision. This is the smallest, simplest shape I can take. Blow gently, and the film becomes a bubble, rounding itself into a sphere, not because it has a preference for beauty, but because physics has given it a rule. The surface of the bubble is pulled tight by surface tension, a force created because water molecules at the surface are attracted more strongly inward and sideways than outward into the air. Soap changes the behavior of the water, making the film flexible and long-lasting. But the underlying tendency remains. The surface tries to reduce its area. A sphere is the shape that encloses the most volume with the least surface area. So, when a bubble traps air inside, it naturally becomes round. It is not trying to look perfect. It is trying to spend as little surface energy as possible. That is the first hidden mathematical problem a bubble solves. How to hold space with the smallest skin. And it solves it instantly, without symbols, without calculation, without ever knowing what a sphere is. But the real wonder begins when bubbles meet each other. One bubble alone becomes a sphere, but two bubbles pressed together flatten where they touch, creating a shared wall. That shared wall is not random. It forms because the bubbles can reduce their total surface area by sharing a boundary, instead of each keeping a full separate surface. If the bubbles are the same size, the wall between them is nearly flat. If one bubble is smaller than the other, the wall curves toward the larger bubble because the smaller bubble has higher internal pressure. This pressure difference comes from the tighter curvature of the smaller bubble's surface. The smaller the bubble, the more its surface tension squeezes inward, so the pressure inside becomes greater. That is why tiny bubbles can shrink and disappear into larger ones in foams over time. The air inside them slowly diffuses through the film, and the foam rearranges itself. Even something as playful as bath foam is quietly changing because curved surfaces, pressure, and surface tension are negotiating with one another. When three soap films meet, they do not usually meet at any angle they like. They tend to meet in a balanced arrangement, often at equal angles, because that is the most stable way for the tensions in the films to pull against one another. In three-dimensional foams, edges and junctions follow similar balance rules. These are known as Plato's laws, named after the scientist Joseph Plato, who studied soap films in the 19th century. They show that bubbles are not chaotic little pockets of air. They are physical demonstrations of minimum energy geometry. The foam is always trying to simplify itself, to reduce wasted surface, to find balance among competing pulls. That is why soap films can create shapes called minimal surfaces. Surfaces that locally use the least area while fitting their boundaries. Stretch a soap film across a wire frame, and it will often choose a shape that is difficult for a person to predict by intuition alone. A cube-shaped wireframe, for example, does not simply get 6 flat square films like invisible walls. The Vortices film can pull inward, connect through the center, and create a surprising structure that reduces area. The soap film finds the form by physics. Every tiny part of the surface moves until the pulling forces balance. If one part has too much curvature or tension imbalance, it shifts. If another part can reduce the total area by sliding inward, it does. The result looks like a solved problem because in a physical sense, it is. This is why soap films have fascinated mathematicians, architects, engineers, and artists. They offer a way to see solutions rather than only calculate them. Before computers became powerful, physical models of soap films were sometimes used to explore efficient shapes. If you wanted to understand how a surface might span a complicated boundary with minimal area, soap could give you a natural answer. It would not always be the final engineering solution, because real buildings need strength, materials, weather, resistance, and safety, but it could reveal efficient forms that human imagination might miss. Bubbles also connect to another famous problem: how to divide space into cells while using as little surface area as possible. Foam is full of compartments, and nature often faces similar challenges. Living tissues, plant cells, insect nests, and materials with cellular structure often involve packing, boundaries, and efficient use of space. For a long time, people wondered what arrangement of equal volume cells would fill space with the least total surface area. Lord Kelvin proposed one solution in the 19th century, using a repeating structure based on a modified 14-faced shape. More than a century later, the Weyerphelan structure was found to use slightly less surface area, showing that even bubbles can lead us into deep mathematical territory where the best answer is not obvious. This does not mean foam consciously knows the Weyerphelan structure, or that every foam becomes the perfect mathematical ideal. Real foams are affected by gravity, drainage, evaporation, impurities, bubble sizes, and time. But the direction of their behavior is still meaningful. They tend toward lower energy. They rearrange, they coarsen, their films thin, their bubbles merge, their walls shift, and their geometry slowly evolves. A foam is like a crowd trying to make more room by sharing boundaries efficiently. Each bubble is trapped by its neighbors, yet all of them together keep adjusting the architecture of the whole. What makes this so beautiful is that bubbles solve by becoming. A human solves a math problem by stepping outside it, representing it on paper, and thinking about it. A bubble solves by physically taking the shape that the forces demand. Its answer is not written in ink, it is the shape itself. This teaches something important about the relationship between mathematics and nature. Mathematics is not only a language humans invented to describe reality from a distance. Sometimes reality behaves in ways that make mathematical principles visible before we put them into words. The bubble rounds itself before we explain why a sphere is efficient. The film spans a wireframe before we name it a minimal surface. The foam rearranges before we write down the rules of surface energy. Nature is not doing schoolwork, but it is following constraints, and constraints often produce order. This is why a child can blow a bubble and accidentally create a lesson in geometry, energy, pressure, and optimization. The bubble's delicacy is part of the lesson. It is powerful enough to reveal a deep principle, but fragile enough to vanish with a touch. Its rainbow colors come from light reflecting from the front and back surfaces of the thin film, interfering in different ways depending on thickness. Those shifting colors show that the film is not uniform. It drains under gravity, moves with air currents, thins, thickens, and eventually breaks when it becomes too unstable. So even while the bubble is solving one problem, it is losing another battle against time. It finds an efficient form, but not a permanent one. And perhaps that is why bubbles feel so strangely meaningful. They are perfect without lasting. They are intelligent without thought. They are mathematical without numbers. They show that beauty can arise when a system is simply allowed to settle toward balance. So the next time you see a bubble floating through the air, try not to see it as only a toy or a fragile shimmer. See it as a tiny physical solution, a rounded answer to a question about area and volume, a soft wall balancing pressure, a film minimizing energy, a temporary geometry written in water and soap. And when it bursts, it has not failed. It has completed its brief demonstration. For a few seconds, it showed you that the universe can solve problems, not by thinking, but by obeying its own quiet rules so gracefully that the answer looks like wonder. Why smoke rings hold their shape. A smoke ring survives because it is not really a ring of smoke, but a rolling ring of air carrying smoke along like dye trapped inside a hidden wheel. When you see one drift from a person's mouth, a volcano, a cannon-shaped toy, or even a dolphin blowing a bubble ring underwater, it can look almost impossible. A soft circle moving forward through the air while holding its outline, as if the smoke has found a temporary skeleton. But smoke itself has no strength. It cannot hold a shape the way metal or ice can. The visible grey ring is only a marker, a tracer, showing you the motion of the air inside and around it. What is actually traveling is called a vortex ring, a donut-shaped pattern of rotating fluid. Imagine a small rubber wheel rolling forward, but instead of rubber, the wheel is made of air turning through itself. The air at the center of the ring moves forward, curls around the outer edge, loops backward, and rolls inward again, creating a continuous circulation. Smoke particles become caught in that rotating motion, so they reveal the structure that would otherwise be invisible. The ring holds together because the rotating flow keeps feeding its own shape for a while. It is not frozen. It is constantly moving, constantly rolling, constantly rebuilding the same form as it travels. This is the first strange truth about smoke rings. Their stability comes from motion, not stillness. A ring that stopped moving would not remain a ring for long. It would diffuse, spread, and vanish into the surrounding air. To make a smoke ring, you need a short pulse of fluid pushed through a round opening. When a puff of air exits the mouth or a circular hole, friction and velocity differences appear between the fast-moving puff and the still air around it. The edges of the puff slow and curl backward, while the center keeps moving forward. That curling edge rolls into a vortex ring. The smoke is not being shaped by intention after it leaves. The shape is created at the boundary, where moving air meets slower air. This is why a sharp, quick pulse works better than a long, messy exhale. A smooth, continuous stream becomes a plume, spreading and twisting irregularly. A short pulse has a beginning and an end, and that compact push helps the vortex wrap into a clean ring. The circular opening matters too. It gives the rolling edge a symmetrical starting shape, allowing the vortex to form evenly around the whole puff. If the opening is uneven, the ring may wobble, tilt, break, or form a lopsided loop. So the smoke ring's beauty is not a trick of the smoke. It is the visible result of a carefully timed burst, a boundary, and a rotating flow pattern that nature knows how to make again and again. Once formed, the ring moves forward because of its own rotation. The rolling motion induces movement through the center and around the ring, pulling the structure along. It is a little like the way a rolling tire moves forward, because every part of it is turning. Except here, the tire is not a solid object. It is a pattern in the fluid. The surrounding air is pushed and drawn into motion, and the ring carries some of that air with it. This is why smoke rings can travel much farther than an ordinary cloud of smoke. A loose puff spreads in all directions and quickly loses its identity, but a vortex ring has organized circulation. It resists immediate mixing because its motion keeps the smoky air bundled inside a coherent rotating structure. But this resistance is only temporary. Air is not perfectly smooth, and the ring is not protected from the world. Tiny disturbances grow. The ring stretches, wiggles, interacts with air currents, slows down, loses energy to viscosity, and gradually mixes with the surrounding atmosphere. Eventually, the clean circle frays into turbulence and disappears. Its life is brief because it is a balance, not a solid thing. It holds its shape only while rotation is strong enough to overcome spreading and mixing. This same physics appears far beyond smoke. Underwater bubble rings made by dolphins or divers are also vortex rings, with air forming a visible ring inside water. Some jellyfish and squid move by producing vortex rings as they push water from their bodies, using the rolling fluid structure to help generate thrust. A volcano can produce enormous smoke or steam rings when gas pulses through a circular vent under the right conditions. Even a simple toy air cannon can knock over a cup from across a room by sending an invisible vortex ring through the air. You do not see the ring unless smoke or fog marks it, but the rotating pulse is real enough to carry momentum. This teaches something important. A vortex ring is a shape made of motion that can transport energy and momentum without needing a solid object. The ring is not the material itself. It is the pattern the material is following. That distinction matters because it appears throughout physics and biology. Waves in water are not the same as water traveling long distances. Often the pattern moves more than the individual water molecules do. A crowd wave in a stadium moves around the arena, even though each person only stands and sits. A smoke ring is similar in spirit. The recognizable thing is not a permanent object, but a traveling organization of movement. The smoke lets you see the organization, but the organization belongs to the air. There is also a quiet lesson in why the ring is round. A circular vortex ring is a natural way for a rotating tube of fluid to close on itself. If the vortex had loose ends, those ends would behave differently, interacting strongly with surrounding air and losing coherence more quickly. By forming a closed loop, the rotation has no open endpoint. The circulation wraps around itself, making a self-contained structure that can travel. It is not perfectly permanent, but it is more stable than a broken curl. This is why rings, loops, and closed forms appear so often when fluids organize motion. Closure protects the pattern for a while. The smoke ring is therefore both fragile and efficient, a temporary agreement between motion and symmetry. And because the ring is made from fluid, it can do things solid rings cannot. It can expand as it slows. It can wobble and ripple around its edge. It can leapfrog with another vortex ring, where one ring expands, slows, and allows another to pass through it in a beautiful exchange of motion. Scientists study vortex rings not only because they are mesmerizing, but because they reveal how fluids transport momentum, how turbulence begins, how propulsion works in water and air, and how coherent structures can arise in something as restless as a fluid. The same basic ideas help explain flows around aircraft wings, blood moving through heart valves, jets of fuel mixing with air, and how animals swim or fly by shaping the fluid around them. A smoke ring, then, is not a party trick. It is a small window into one of nature's deep habits, making temporary order out of motion. What makes it so hypnotic is that it seems to have a body, but it is only behavior. It seems to be a thing, but it is really a process. It looks calm because the pattern is organized, yet inside it everything is rolling, turning, and exchanging. That is why it feels almost alive. It is born from a pulse, travels through space, holds itself together through circulation, weakens, frays, and dissolves back into the air that made it. The next time you see a smoke ring drift forward, do not think of it as smoke keeping a perfect circle by chance. See it as a rotating engine made of air, visible only because tiny particles have been caught inside its motion. See it as a soft machine with no parts, a wheel with no surface, a structure that exists only because it keeps moving. For a few seconds, the invisible flow of the world becomes visible, and then the ring fades, not because it was unreal, but because some forms in nature are meant to exist only as long as motion can remember their shape. The strange order, hidden inside random motion. Random motion looks like nature has stopped caring, until you realize that the chaos of countless tiny movements can produce some of the most reliable order in the universe. Look at dust drifting in a sunbeam, steam rising from a cup, perfume spreading across a room, milk curling into coffee, or a crowd of tiny particles suspended in water. And at first the movement seems meaningless, no plan, no direction, no visible pattern worth trusting. But the deeper lesson of physics is that randomness does not always mean disorder in the way we imagine. When enough small things move unpredictably, their individual paths may be impossible to follow, yet their collective behavior can become astonishingly predictable. This is one of the quiet miracles behind everyday reality. A single molecule in the air may dart, collide, turn, speed up, slow down, and change direction so often that its journey becomes almost unreadable. But a room full of air molecules follows dependable rules. It has pressure. It has temperature. It flows from higher pressure toward lower pressure. It carries smells outward. It warms, cools, mixes, and settles into patterns you can measure. The individual motion is chaotic, but the crowd becomes law-like. In other words, order can emerge not because every part is controlled, but because no single part matters enough to dominate the whole. This is what makes statistical thinking so powerful. You may not know what one molecule will do next, but you can know what trillions of them are likely to do together. It is like listening to one person in a stadium shout at random, then listening to the whole stadium roar. One voice may be unpredictable. The crowd has a volume, a rhythm, a pressure of its own. Temperature itself is a perfect example. When you say something is hot, you are not describing a hidden fluid called heat sitting inside it. You are describing, in everyday language, how energetically its particles are moving. In a warm cup of tea, the molecules are jiggling, rotating, colliding, and exchanging energy faster than in a cold drink. You cannot see this motion directly, yet your hand feels the result. The warmth is a large-scale meaning created from countless invisible movements. Pressure works in a similar way. The air in a tire does not push outward because all the molecules have held a meeting and agreed to press on the rubber. They are simply flying around and colliding with the inner walls again and again. Each collision is tiny, but together they create a steady pressure strong enough to hold the tire's shape. This is the strange order hidden inside randomness. Tiny accidents, repeated in enormous numbers, become a stable force. Diffusion is another quiet example. Open a bottle of perfume in one corner of a room, and the scent slowly spreads. Not because the molecules know where to go, but because random motion carries them in all directions. At first, many scent molecules are concentrated near the bottle. As they wander and collide with air molecules, they gradually spread into places where fewer scent molecules exist. No single molecule has a map, but the group produces a direction, from crowded to less crowded, from concentrated to dispersed. This direction is not commanded from above. It emerges from probability. There are simply far more ways for the molecules to be spread out than for them to remain gathered in one corner. That idea reaches into one of the deepest principles in physics. Systems tend to move toward arrangements that are more likely, and more likely often means more mixed, more spread out, more evenly distributed. This is why a drop of ink disperses in water, but does not spontaneously gather itself back into a perfect drop. It is not technically impossible in the deepest sense for all the molecules to return by chance, but it is so unimaginably unlikely that reality never gives it back to you. The arrow of everyday time is hidden in this difference. Eggs break more easily than they unbreak. Smoke spreads more easily than it folds itself back into a match flame. Warm coffee cools in a room more easily than the room's random energy gathers itself to reheat the coffee. The universe is full of microscopic motion that can run in many directions, but at the human scale, probability gives time its familiar one-way feeling. And this is where randomness becomes almost philosophical. What you call the natural direction of things may not always be a command written into every tiny part. Sometimes it is the overwhelming weight of possibilities. The future happens not because every particle chooses it, but because some arrangements are so much more likely than others that they become the path reality almost always takes. Yet randomness does not only lead to spreading and fading. Under the right conditions, it can help create structure. In materials, atoms jiggle constantly, but as a liquid cools, those moving atoms can settle into orderly crystals if conditions allow. In metals, ceramics, ice, and salts, microscopic disorder can gradually give way to repeating arrangements. In living cells, random molecular motion helps bring molecules into contact so reactions can happen. Proteins, enzymes, nutrients, and signaling molecules do not always move like tiny machines on rails. Many are buffeted by thermal motion, wandering, colliding, binding, separating, and trying again. Life does not eliminate randomness, it uses it. Cells create boundaries, gradients, and chemical rules that turn random encounters into useful outcomes. A molecule may wander blindly, but if it fits the right receptor, a signal begins. A protein may fold through many possible shapes, but physical attractions guide it toward a stable form. A cell may be noisy inside, yet from that noise comes repair, growth, motion, and response. This does not mean life is accidental in a shallow sense. It means life is skilled at harvesting chance. It builds systems where random motion is not wasted but filtered. Some possibilities are rejected, others are amplified, and over time, order appears. You can see a similar idea in crowds, traffic, weather, markets, and even human behavior, though those systems are far more complex and involve choices, feedback, and information. The broad lesson remains. When many small, unpredictable actions interact, patterns can arise that no single part intended. Traffic jams can form without an accident. Waves of applause can synchronize in an audience. Birds can flock without one bird holding a blueprint. The world often organizes itself through local interactions, not central control. Physics gives this idea its simplest foundation in moving particles, but the pattern repeats in many places. Individual unpredictability, collective structure. Still, there is a warning here. Randomness can create order, but not every apparent pattern has deep meaning. The human brain loves to find shapes, stories, and signals even in noise. We see faces in clouds, messages in coincidences, destiny in chance events. Science asks us to be patient. Some order is real, some is imagined, and the difference matters. The patterns hidden inside random motion are not mystical instructions. They are physical tendencies, measurable behaviors, and statistical truths. The beauty is stronger because it is honest. No molecule needs intention for diffusion to occur. No atom needs awareness for temperature to exist. No particle needs a plan for pressure to arise. Order can emerge from blindness, and that may be more astonishing than any fantasy. It means the universe can build reliable experience from restless uncertainty. It means stillness is often a mask worn by motion too small to see. The table in front of you appears calm, but its atoms vibrate. The air around you feels empty, but molecules are colliding constantly. Your body feels like a stable self, but inside it countless microscopic processes are moving, mixing, reacting, correcting, and renewing. You are not alive because randomness disappeared from you. You are alive because your body has learned how to keep useful order while surrounded by motion that never stops. So the next time something looks random, do not rush to dismiss it as meaningless. Look more gently. Ask what happens when the motion is repeated millions, billions, or trillions of times. Ask what patterns appear only when you stop following one particle and begin listening to the whole. The secret is not that chaos is secretly neat, or that disorder is only an illusion. The secret is subtler. Randomness and order are not enemies. They are partners. One provides the raw motion, the endless variation, the restless testing of possibilities. The other appears when those possibilities gather into something stable enough to feel, measure, or live inside. And perhaps this is why the world can feel both uncertain and dependable at once. Beneath every quiet surface, tiny motions are wandering without a map. Yet from their wandering comes pressure, warmth, diffusion, growth, balance, and time's one-way flow. The universe is not still, and it is not fully predictable in its smallest details. But somehow, from all that trembling, it builds the calm stage on which your life unfolds. Why ice is slipperier than it should be. Ice feels like a solid floor that has forgotten how to hold you. And that is exactly why it is so strange. It is hard enough to support your weight, yet under your foot it can behave as if a hidden liquid is waiting at the surface. You step onto it expecting ordinary friction. The quiet grip you get from stone, wood, or dry pavement. But ice answers differently. Your shoe slides, your balance vanishes, and for a moment your body learns a lesson that physics has been arguing about for a long time. Ice is not slippery for one simple reason. The old explanation many people learned is that pressure from your foot melts a thin layer of ice, creating water, and that water makes you slide. This sounds neat, but it is not enough. Ordinary pressure from shoes is usually not strong enough to melt ice significantly at common outdoor temperatures, especially when the ice is very cold. Ice can be slippery even when pressure melting is too weak to explain it. So the real story is more subtle and more interesting. Ice is slippery because several effects work together. Its surface can have a very thin, disordered layer that behaves somewhat like liquid. Friction can create tiny amounts of meltwater as you move, and the smoothness or roughness of the ice changes how much grip your foot or skate can find. The surface of ice is not exactly like the interior. Deep inside, water molecules are arranged in a crystal structure, locked into a repeating pattern. But at the surface, the molecules have fewer neighbors holding them in place, so they can be less orderly, more mobile, more restless. Scientists often describe this as a quasi-liquid layer, not a puddle you can see, not a thick film like rainwater, but a microscopic region where the molecules behave more freely than they do in solid ice. This layer can exist even below freezing, though its thickness depends strongly on temperature. Near the melting point, it becomes more significant. At much colder temperatures, it becomes thinner, and ice can feel less slippery. This is why extremely cold ice may squeak underfoot and offer more grip than ice near 0 degrees Celsius. Anyone who has walked on different kinds of frozen ground has felt this without needing to name it. Some ice is glassy and treacherous, some is dry and harsh, some grips more than expected, and some turns the whole world into a trap. Temperature changes the personality of ice, but the surface layer alone is still not the whole story. Movement matters. When your shoe, sled, tire, or skate moves across ice, friction turns some motion into heat right at the contact area. That local heating can create or thicken a tiny film of water, especially when the ice is close to its melting point. The faster you move, the more the contact conditions change. In ice skating, a skate blade concentrates weight into a narrow line and also glides with friction, helping create conditions for smooth motion. But modern research suggests skating is not simply the blade melts ice by pressure. It is a combination of pressure, frictional heating, surface mobility, and the shape of the blade interacting with the ice. The skate also cuts slightly into the surface, creating a narrow track and allowing the skater to push sideways against the ice. That is why skating is not just sliding helplessly. It is controlled slipping, a partnership between low friction and sharp edges. A person on flat shoes slips because they lack that same controlled edge. The ice offers too little resistance in the direction of motion, and the foot moves before the body can correct. This is also why rough ice can be safer than polished ice. Tiny bumps, scratches, snow grains, salt, sand, or textured surfaces interrupt smooth sliding and give your shoe something to grip. Fresh snow on top of ice can sometimes help, because the crystals create texture, but packed snow can become slick again when compressed and smoothed. Ice is not one surface. It is many possible surfaces, changing with temperature, pressure, sunlight, impurities, and traffic. A sidewalk after freezing rain is dangerous because the water has formed a smooth, continuous glaze over the ground. A frozen lake may be slippery in one place and rough in another. A skating rink is carefully maintained so its surface stays smooth enough for gliding, but firm enough for control. Even the presence of salt changes the story because salt lowers the freezing point of water, helping create brine that can melt or soften ice, depending on conditions. That is why roads are salted in winter, though salt becomes less effective in very cold weather. The slipperiness of ice, then, is not a magic property. It is an unstable balance between solid and liquid behavior, between grip and glide, between crystal order and surface disorder. And this balance exists because water is already one of the strangest ordinary substances on Earth. Most materials become denser when they freeze, but ice is less dense than liquid water, which is why it floats. That floating ice insulates lakes from above and helps aquatic life survive winter below. The same molecular features that make water expand when freezing also give ice its crystal structure and unusual surface behavior. So when you slip on ice, you are not just experiencing a winter inconvenience. You are meeting the consequences of hydrogen bonding, molecular motion, phase behavior, and friction in one sudden loss of balance. It is almost funny. A whole universe of microscopic physics appears as one embarrassing moment on a sidewalk. But there is something deeper in it too. Ice teaches you that a surface can deceive you. It can look firm but behave like a threshold. It can hold a car, a skater, a lake, a mountain glacier, and still betray a careless step. It reminds you that solidity is not always the same as safety, and smoothness is not always gentle. The most dangerous ice is often the ice that looks simplest. Clear, quiet, polished, almost invisible. Black ice on a road is frightening because it hides itself, blending with asphalt until tires meet it and discover too late that friction has been taken away. Your senses tell you ground, but physics says not enough grip. And in that small mismatch between expectation and reality, accidents happen. So the next time you see ice shining under a winter sky, do not think of it as merely frozen water. Think of it as a surface balanced on the edge of two worlds. Beneath it is a crystal. At its skin is molecular restlessness. Under movement, friction can wake a trace of liquid. Under cold, it can harden into a rougher, less forgiving dryness. Under a skate, it becomes a path. Under a shoe, it can become a warning. Ice is slipperier than it feels like it should be because it is not simply solid in the way your body expects. It is a frozen structure with a surface that remains strangely alive. And when you step onto it, the hidden physics of that surface decides whether you glide, grip, or fall. The science of resonance in bridges and glass. A bridge can look immovable, and a wine glass can look delicate, yet both are secretly waiting to be asked the right question in the right rhythm. Tap a glass gently and it sings with a clear tone. Not because the glass contains music, but because its shape, thickness, material, and rim allow it to vibrate in a preferred way. Push a playground swing at random times and nothing much happens, but push it at just the right moment, again and again, and a small effort grows into a large motion. That is resonance. The quiet amplification that happens when repeated energy arrives in step with a system's natural vibration. It is not magic, and it is not simply sound becoming powerful. It is timing. It is rhythm meeting structure. Every object that can vibrate has natural frequencies, patterns it prefers when disturbed. A ruler hanging off a desk, a guitar string, a building in the wind, a bridge under footsteps, a glass rim touched by a wet finger. Even parts of your own body can respond more strongly to some frequencies than to others. Most of the time, everyday vibrations fade quickly because materials bend, rub, heat slightly, and lose energy. But when a repeated push keeps arriving at the right pace, each push adds to the motion instead of fighting it. The movement grows. At first, it may be small enough to ignore. Then it becomes visible. Then, in extreme cases, it can become dangerous. This is why resonance is both useful and frightening. It shows how small forces can become large when they are patiently repeated with the right timing. A wine glass gives one of the clearest examples. When you flick it, the glass vibrates, and the air carries that vibration to your ear as a tone. The pitch depends on the glass's geometry, thickness, and stiffness. If a singer produces the same pitch loudly and steadily enough, the sound waves can feed energy into the glass's natural vibration. The glass begins to flex in tiny motions, often too small to see at first. If the sound is strong, stable, and accurately matched, and if the glass has small flaws or is thin enough, those vibrations can grow until the stress becomes too much and the glass cracks or shatters. But this is much harder than movies make it seem. A normal voice in a normal room will not casually explode a glass on command. The singer must match the glass's resonant frequency very closely and produce enough volume, often with amplification or exceptional vocal power. The glass itself matters too. A thick, strong glass may survive. A fragile crystal glass may respond more dramatically. Tiny imperfections can become places where stress concentrates. And once a crack begins, the structure fails quickly. So the real lesson is not that sound has supernatural destructive power. The lesson is that structure has memory. The glass remembers certain patterns of motion better than others. And when the outside world keeps feeding that pattern, weakness can reveal itself. Bridges tell the same story, but on a scale where the consequences can be enormous. A bridge is not just a rigid line across space. It is an elastic structure. It bends, sways, expands, contracts, twists, and vibrates under wind, traffic, footsteps, temperature changes, and its own weight. Engineers know this, so they design bridges not only to hold loads, but to manage motion. A bridge can have several natural modes. It may move up and down, side to side, twist along its length, or combine these motions in complex ways. If repeated forces match one of those modes, the motion can grow. This is why soldiers are often told to break step when crossing a bridge. Marching in perfect rhythm can create repeated pulses that line up too neatly with the bridge's natural movement. The danger is not that footsteps are individually powerful. It is that synchronized timing can keep adding energy. One footstep is small. Thousands of coordinated footsteps can become a mechanical chant. The bridge hears rhythm as force. A famous modern example is London's Millennium Bridge, which opened in 2000 and quickly became known for an unexpected side-to-side wobble when crowds walked across it. The walkers did not intentionally shake the bridge. Instead, as the bridge moved slightly sideways, people naturally adjusted their steps to keep balance, and those adjustments unintentionally synchronized with the bridge's motion. The crowd and bridge entered a feedback loop. The bridge swayed, people stepped with the sway, their steps added more sideways force, and the sway increased. Engineers solved the problem by adding dampers, devices that absorb energy and reduce motion. Dampers are like quiet protectors against resonance. They do not make the forces disappear. They drain energy from the vibration before it grows too large. Skyscrapers use similar ideas. Some tall buildings contain tuned mass dampers, large moving weights designed to sway against the building's motion during wind or earthquakes, reducing uncomfortable or dangerous movement. In this sense, engineering is not always about preventing motion. Often, it is about allowing motion safely, guiding it, limiting it, and giving it somewhere to go. Another famous bridge story is the Tacoma Narrows Bridge collapse in 1940. Often casually described as a simple resonance disaster, the truth is more subtle. The bridge did not fall merely because wind pushed it at one matching rhythm like a child on a swing. Its collapse involved aeroelastic flutter, a self-feeding interaction between wind and the twisting motion of the bridge deck. The wind did not just apply a repeated external push. The bridge's own movement changed the airflow in a way that fed energy back into the motion. The twisting grew until the structure could not survive. This distinction matters because real science becomes more powerful when we resist the easy myth. Resonance was part of the broader family of vibration problems. But the central danger was a coupling between structure and wind. The bridge and the air became partners in instability. That is a more haunting idea than the simplified version. Sometimes disaster begins when a structure's motion changes the forces acting on it, and those changed forces amplify the motion further. The system starts answering itself. Resonance also explains why some rooms boom at certain bass notes, why a car may rattle only at one engine speed, why washing machines shake violently when an unbalanced load spins at the wrong rate, and why musical instruments can fill a space with rich sound. A guitar body resonates to make string vibrations louder. A drum head resonates when struck. A violin's wooden body shapes and amplifies the vibration of its strings. Without resonance, instruments would sound thin and weak. So resonance is not only a threat, it is the reason small vibrations can become music. The same principle that can shatter glass can also give a cello its warmth. The same timing that can trouble a bridge can let a child rise higher on a swing with almost no effort. Nature does not label resonance as good or bad. It simply says, if energy arrives in rhythm with a system's preferred motion, the response can grow. Whether that growth becomes beauty, usefulness, discomfort, or collapse depends on the structure, the strength of the input, and the amount of damping. Damping is the quiet opposite of resonance. It is the way systems lose energy, through friction, internal resistance, air drag, heat, and design features that absorb motion. A bell rings because it has low damping. It keeps vibrating after being struck. A pillow does not ring because its soft material quickly turns motion into heat and disorder. A bridge with good damping may move, but the motion fades instead of growing. A glass with enough internal resistance may vibrate without breaking. Every vibrating thing lives between amplification and loss, between rhythm feeding motion and material draining it away. And perhaps this is why resonance feels so meaningful beyond the equations. It teaches that strength is not only about how much force arrives, but about when it arrives. A badly timed push may do almost nothing. A perfectly timed small push may change everything. In life too, repetition can build power quietly. A thought repeated becomes a belief. A habit repeated becomes a character. A stress repeated without release can become damage. A kindness repeated at the right moments can become trust. Physics does not prove these human truths, but it gives us a beautiful mirror for them. Systems respond to rhythm. Structures remember timing. Small energies accumulate when they arrive in harmony. So the next time you hear a glass ring, feel a bridge tremble faintly under traffic, or watch a swing rise higher with each gentle push, remember that the world is full of hidden preferred motions. Nothing is completely still. Every structure has ways it wants to move, songs it can answer, rhythms that can wake it. Resonance is what happens when the outside world finds that private rhythm and keeps speaking it. Sometimes the result is music, sometimes it is motion, sometimes it is warning, and sometimes, if the rhythm is strong enough and the structure has nowhere to release the growing energy, the quiet vibration becomes the moment when something solid finally reveals how fragile it has always been. Why dust can reveal. Invisible air rivers. Dust is the closest most of us ever come to seeing air move, because the air itself is invisible. But dust turns its hidden paths into slow, drifting handwriting. In a quiet room, you may think the air is still, but place that room in a beam of sunlight, and suddenly the stillness breaks open. Tiny particles float, rise, fall, spin, pause, and slide sideways as if they are following roads no one drew. They are not moving by magic, and they are not alive. They are passengers. What they reveal is that air inside a room is never a blank emptiness. It has currents, loops, pockets, gentle streams, and invisible rivers created by temperature differences, movement, ventilation, breathing, electronics, windows, doors, and even the warmth of your own body. Dust becomes visible evidence of those flows because the particles are small enough to be carried by air, but large enough to scatter light into your eyes. A sunbeam does not create the dust, it gives the dust a stage. It is like throwing pale seeds into a dark river and suddenly discovering that the water was moving all along. The first hidden driver is heat. Warm air tends to rise because it becomes slightly less dense than cooler air around it. This is why the air above a heater, a laptop, a lamp, a cup of tea, or a sunlit floor can begin to lift dust upward in soft columns. You may not feel that motion on your skin, but the particles show it. They climb slowly, curve, spread, and then settle into the larger circulation of the room. Near a cold window, air can cool, become denser, and sink downward, creating a descending flow that may pull dust toward the floor. So even without a fan, a room can have a quiet cycle. Warm air rising in one place, cooler air sinking in another, and sideways return flows connecting them. This is called convection, and it is one of the main ways air organizes itself indoors. It is not dramatic like wind outside, but it is constant enough to matter. It moves smells, moisture, smoke, airborne particles, and heat. It helps explain why one corner of a room feels warmer, why dust gathers near vents or baseboards, why curtains can shift slightly near a window, and why a room can feel stale even when it looks calm. Air does not need to roar to travel. It can move like a slow tide around furniture, along walls, under doors, and across ceilings. Doors and windows add another layer. Open a door quickly, and you create a pressure change, pushing air ahead and pulling air behind. Dust in the doorway may swirl, because the moving door acts like a paddle in an invisible fluid. Crack a window on a cooler day, and air may enter low and leave high, or the reverse, depending on indoor and outdoor temperature, wind direction, and pressure. A ventilation system can create steady streams that carry particles across the room, but the path is rarely straight. Air bends around obstacles. It separates at sharp corners. It curls behind objects. It slows near surfaces because of friction. A bookshelf, a couch, a person standing still, even a hanging coat can shape the flow like rocks shaping water in a shallow stream. This is why dust often collects in strange places. Under beds, along wall edges, behind electronics, on fan blades, inside vents, and in quiet corners where air slows down enough for particles to settle. Dust deposits are like long-term maps of airflow. They show where the invisible rivers lost strength and dropped what they were carrying. The size of the particle matters too. Larger dust grains fall faster because gravity pulls them down more effectively compared with the air's ability to hold them up. Very tiny particles can remain suspended much longer, especially if the air is moving. Some particles follow currents faithfully, while heavier ones drift downward through them. This is why dust in sunlight can seem to float dreamily, while heavier debris lands quickly. The particle's shape, density, and surface also influence how it moves. A tiny fiber from clothing may tumble differently from a grain of pollen or a speck of skin. Air is not carrying one kind of thing. It is carrying a mixed crowd, each member responding slightly differently to gravity, drag, and turbulence. Turbulence is where the hidden rivers become especially beautiful. When air moves smoothly, particles may drift in graceful lines. But when flows meet, speed up, slow down, or pass around obstacles, they can form eddies, small rotating motions that twist dust into curls. You see this when sunlight reveals particles spiraling after someone walks through a room, when a fan turns on, or when a warm surface sends air upward into cooler surroundings. The air is mixing itself. It folds one layer into another, breaks smooth streams into smaller swirls, then lets those swirls fade. Turbulence can look random, but it has structure at many scales. Large motions break into smaller ones, and smaller ones into still smaller ones, until the energy is finally lost as heat. Dust lets you watch a tiny part of that cascade. It makes the room feel less like a container and more like weather. In fact, every indoor space has its own microclimate. The air around your face is warmed and moved by your breathing. Your body creates a faint thermal plume, a gentle upward flow caused by your body heat. This plume can carry tiny particles upward from your clothes and skin, and it can also influence what you inhale from the air around you. When people gather in a room, each body becomes a warm source. Each breath a small jet, each movement a disturbance. This does not mean you should fear every speck of dust, but it does mean indoor air is dynamic and shared. Good ventilation matters because it changes how particles, humidity, and carbon dioxide build up or leave. Filtration matters because it can remove some airborne particles from circulation. Cleaning matters because settled dust can be lifted again by movement. The invisible rivers are not only poetic, they affect comfort, health, and the way buildings breathe. Even outdoors, dust reveals air on larger scales. Desert dust can travel across oceans. Pollen rides seasonal winds. Smoke from wildfires can cross countries. Volcanic ash can spread through the atmosphere and affect aviation. The same basic idea you see in a sunbeam scales upward. Particles make air movement visible. Scientists use tracers, smoke, aerosols, and tiny droplets to study airflow in laboratories, around vehicles, inside buildings, and across landscapes. Engineers may release smoke in wind tunnels to see how air moves around a wing or car body. Building designers study airflow to understand ventilation. Meteorologists track dust and aerosols to learn how air masses travel. The humble dust mote in your bedroom belongs to the same family of evidence as satellite images of dust plumes crossing the Atlantic. It is all matter-revealing motion, and perhaps that is why this simple sight feels strangely calming. Dust in sunlight looks slow, almost weightless, but it is showing you a truth your eyes usually miss. You live inside a moving fluid. The air is not a passive background. It is a restless medium that carries warmth, scent, moisture, sound, particles, and breath. It enters, leaves, rises, sinks, curls, and settles. Your room is not merely a box filled with air. It is a landscape of invisible streams. The dust is only the messenger. So the next time a beam of light cuts across a room and you see tiny particles drifting through it, do not dismiss them as dirt alone. Watch their paths. See how some rise, some fall, some hesitate, some spin, some vanish into darkness. They are tracing the hidden rivers around you, showing that even the quietest air has direction, memory, and motion. And in that gentle drifting, the ordinary room becomes a weather system small enough to live inside, but complex enough to remind you that stillness is often just movement too subtle to see. The silent electricity passing across your skin. Your skin is not just a boundary between you and the world. It is a living electrical landscape, quietly gaining charge, losing charge, conducting tiny signals, resisting others, and turning invisible contact into sensations you barely notice until a spark suddenly snaps from your fingertip. Most of the time, this surface electricity is silent. You walk across a carpet, pull off a sweater, slide into a car seat, touch a metal doorknob, and only when the shock arrives do you realize that something had been building all along. That small sting is not a mystery, and it is not your body creating lightning from nowhere. It is static electricity, a separation of electric charge that often begins when two materials rub, touch, and separate. Electrons can move from one surface to another depending on the materials involved, and after enough contact and separation, one surface may hold extra negative charge while the other is left more positive. Your skin, your clothes, your shoes, the floor, the air, and the objects around you all participate in this quiet exchange. The reason you do not always feel it is that the charge may be small, spread out, or slowly leaking away through moisture in the air or through your body's contact with other surfaces. But under dry conditions, especially in winter or in air-conditioned rooms, charge can build more easily because dry air is a poor helper for letting charge dissipate. Moisture makes surfaces slightly more conductive, giving charge a path to escape. When the air is dry, the charge lingers, waiting for a bridge. Then your finger approaches metal. The electric field across the tiny gap becomes strong enough. Air molecules briefly ionize, and a spark jumps. For a fraction of a second, air becomes a path. The crack you hear and the sting you feel are the sudden equalizing of charge, a tiny discharge between your body and the object. It is small compared with lightning, but it belongs to the same family of events, separated charge seeking balance through a conducting path. Your skin plays a complicated role in this because it is not a simple wire and not a perfect insulator. The outermost layer, the stratum corneum, is made of dead flattened cells and lipids, and when dry it resists electric current quite strongly. But beneath it, your tissues contain salty fluids, and salty water conducts electricity far better because ions can move through it. This is why wet skin is much more conductive than dry skin, and why electrical safety is so serious around water. A current that might be poorly conducted across dry skin can become far more dangerous when the skin is wet, broken, or in firm contact with a conductor. The body is electrical, but that does not mean all electricity is harmless. Your nerves and heart rely on carefully controlled biological signals, while outside currents can interfere with those systems if they are strong enough and pass through the wrong paths. The tiny static shock from a doorknob is usually startling rather than dangerous because it is brief and carries very little total charge. But larger electrical exposures are a completely different matter. This distinction is important because the real science is not about fear. It is about scale, path, duration, and control. Your body can safely use delicate internal electrical signals every moment because cells manage them with membranes, channels, and chemical gradients. But uncontrolled electricity from outside does not respect those boundaries. Still, at the surface of everyday life, most skin electricity is subtle, ordinary, and surprisingly informative. Your skin's electrical properties change with sweat, moisture, emotional arousal, temperature, and contact. When you feel nervous, your sweat glands can become more active, especially in the palms and fingers. Even a tiny increase in moisture can lower skin resistance and make the skin conduct electricity slightly better. This is the basis of what is often called galvanic skin response or electrodermal activity. It does not read your mind, and it cannot reveal truth by itself, despite the dramatic way lie detectors are often portrayed. But it can measure changes in skin conductance linked to arousal, stress, attention, surprise, or emotional intensity. In other words, your skin can become electrically different when your inner state changes. A fear you do not speak may still alter the tiny conductivity of your hands. A sudden sound, a memory, a difficult question, or a moment of anticipation can leave a measurable trace on the surface of the body. The skin becomes not just a covering, but a quiet instrument that reflects the nervous system's state. This is also why touchscreens respond to you. Many modern phone screens are capacitive, meaning they sense changes in an electric field near the glass. Your finger, because your body can conduct charge and interact with that field, changes the screen's electrical pattern when you touch it. The device does not feel your finger in a human sense. It detects an electrical disturbance and calculates where it happened. If you wear thick gloves that do not conduct well, the screen may not respond because the electrical connection between your body and the screen is blocked. Special touchscreen gloves work by using conductive fibers to let that interaction happen. So one of the most ordinary modern gestures, tapping a screen, depends on the silent electrical nature of your skin. You are not just pressing glass, you are altering a field. Static electricity can also make your skin and hair behave in ways that feel almost playful. Rub a balloon on hair, and some hairs rise toward it, because charge separation creates attraction. Individual hairs may repel each other if they carry similar charge, making them spread apart. Clothes can cling to your skin after tumbling in a dryer, because different fabrics exchange charge and now attract. Plastic wrap grips a surface partly because of electrostatic attraction. Dust can stick to screens, shelves, or skin for similar reasons. These effects are small, but they show that electricity is not only inside wires and storms. It is woven through friction, fabric, plastic, skin, air, and ordinary touch. In industrial and electronic settings, these small charges matter greatly. A static discharge too tiny for you to notice can damage sensitive electronic components, which is why people working with delicate circuits may use grounding straps, anti-static mats, and careful humidity control. The human body can carry enough static charge to harm microelectronics even when the person feels nothing. Again, the lesson is scale. What is too small for your nerves may still be large enough for a tiny circuit. What is harmless as a brief fingertip spark may be catastrophic to a fragile chip. Electricity is not one thing in one form. It is a set of relationships between charge, material, distance, and path. Your skin sits in the middle of these relationships every day. It protects you, senses the world, holds moisture, releases sweat, sheds cells, gathers charge, conducts a little, resists a lot, and changes its electrical behavior with your environment and emotions. It is both shield and sensor, barrier and bridge. And perhaps the strangest part is how often you mistake this for nothing. The sweater crackling in the dark, the tiny snap from a car door, the phone recognizing your fingertip, the palm becoming more conductive when you are anxious, the dry winter air making every touch feel sharper. All of it belongs to the same hidden story. Your surface is electrically alive in ways that do not need drama to be real. So the next time a small spark jumps from your hand, pause before brushing it off as a simple annoyance. It is a message from a world of charges you are carrying without knowing. It tells you that contact is never merely contact, that skin is not a passive wrapping, and that the boundary of your body is constantly negotiating with materials, moisture, air, and fields around it. You move through life thinking your skin only feels the world, but sometimes, quietly, the world is also reading your skin. Why cracks follow hidden stress maps? A crack is not a random line drawn by damage. It is a path chosen by invisible stress long before the surface finally breaks. You see the finished shape after it appears, the jagged split in a phone screen, the branching fracture in dry mud, the thin line crawling across old paint, the sudden break in a ceramic cup, the spreading star in a windshield after a tiny stone hits it. To the eye, it can look accidental, almost careless, as if matter simply gave up in a messy direction. But most cracks are not wandering blindly. They are following a hidden map of weakness, tension, pressure, structure, and history inside the material. Before anything breaks, forces are already moving through it. Pull on a piece of plastic, bend a branch, heat a glass unevenly, dry a layer of clay, press on concrete, or strike a stone, and the material does not feel the force equally everywhere. Some regions carry more stress than others. Some corners, scratches, pores, bubbles, and tiny defects become places where stress gathers. These places are called stress concentrators, and they matter because breaking often begins where force has been quietly amplified. A perfectly smooth, flawless material could be much stronger than the objects we use in real life, but real materials are never perfect. They contain microscopic cracks, uneven grains, trapped impurities, tiny holes, surface scratches, and invisible changes left by cooling, shaping, bending, drying, or aging. A crack usually begins when one of these small flaws becomes the easiest place for the material to release stored energy. That is the key idea. Cracking is not just destruction. It is energy finding a route. When a material is under stress, energy is stored inside it, like tension in a stretched rubber band or pressure in a bent ruler. If a crack grows, it can release some of that energy, but it also has to create new surfaces, and creating new surfaces costs energy. A crack advances when the release is worth the cost. This is why some cracks stop and others race forward. A tiny crack may sit quietly for years because the stress is not enough to drive it. Then a change arrives. More weight, a colder night, a sharp impact, repeated bending, drying shrinkage, or heat on one side and cold on the other. Suddenly the balance shifts and the crack begins to move. Once it moves, its sharp tip becomes extremely important. The end of a crack concentrates stress strongly because the force lines crowd around that narrow point. The sharper the crack tip, the more intensely stress gathers there. This is why a small scratch can weaken glass. Why a drilled round hole at the end of a crack can sometimes slow its growth. And why engineers design rounded corners instead of sharp internal corners when they want parts to survive. Sharp corners invite stress to gather. Rounded shapes spread it more gently. Matter in this sense has preferences. It does not like sudden changes in shape when force is moving through it. The crack's path follows the direction where the material can release stress most easily, but that path is shaped by the material's internal structure. In glass, cracks can travel quickly because glass is brittle. It does not bend much before breaking, so when stress becomes too high, the fracture can move with startling speed. That spiderweb pattern on a windshield forms because the impact sends stress waves through the glass, and cracks branch as the energy spreads outward. Laminated windshield glass is designed with a plastic layer between sheets so that it holds together instead of exploding into loose shards. Tempered glass behaves differently. It is made by cooling the outside faster than the inside, leaving the surface in compression and the interior in tension. This makes it strong against many surface cracks, but when it finally fails, the stored internal stress can make it shatter into many small pieces rather than large, sharp fragments. So even the way glass breaks is a memory of how it was made. Ceramics, stone, and concrete have their own crack stories. They are strong under compression, but often weak under tension. Push down on concrete and it can carry enormous loads, but pull or bend it the wrong way and cracks can open. That is why reinforced concrete uses steel bars inside. Concrete handles compression well, while steel helps carry tension. A sidewalk crack may begin because the ground shifts. Roots grow, water freezes and expands in tiny gaps. Or temperature changes make the slab expand and contract. The line you see is the visible ending of slow, invisible negotiations between material, weather, ground, and time. Mud cracks tell another version. When wet mud dries, it shrinks, but the mud is stuck to the ground beneath it and to neighboring regions beside it, so it cannot shrink freely everywhere. Tension builds. Eventually, the mud splits to relieve that tension, often forming polygon-like patterns because cracks divide the surface into regions that can shrink more easily. The pattern is not decoration. It is the material solving a drying problem by breaking itself into smaller pieces. Paint can crack for similar reasons when layers dry, shrink, age, or respond differently to temperature and moisture. Even wood cracks because its fibers shrink differently depending on direction and moisture content. A log drying out may split from the outside inward because the outer layers lose moisture faster than the inside, building tension that the wood releases along the grain. The grain matters because materials are not always equally strong in every direction. Wood has fibers. Metals have grains. Rocks have layers. Bones have internal structure. A crack often chooses the easier path through these built-in directions. In metals, cracks can grow slowly under repeated stress, a process called fatigue. A metal part may survive one load easily, but if it is bent, shaken, or loaded again and again, Microscopic cracks can form and grow with each cycle. This is why aircraft, bridges, engines, and machines must be inspected. Failure may not come from one dramatic overload, but from many small repetitions that slowly extend a crack until the remaining material can no longer carry the load. The final break looks sudden, but the story may have been unfolding quietly for months or years. This is one of the most unsettling truths about cracks. The visible failure is often the last sentence, not the first. The hidden map was already there. Engineers study cracks because they are warnings written in the language of stress. A crack's direction, branching, speed, width, and surface texture can reveal what kind of force caused it. Did the material bend? Was it pulled apart? Was there an impact? Did it fail slowly through fatigue or suddenly through overload? Fracture surfaces can become evidence, almost like a crime scene in matter. The break tells a story about force and weakness if you know how to read it. But cracks are not only signs of failure. In nature, cracking can be part of renewal and function. Seeds crack open as they germinate. Rock cracks allow water to enter, freeze, widen gaps, and help form soil over long times. Earth's crust fractures along faults, releasing stress as earthquakes when the built-up strain becomes too great. Your own skin can crack when too dry because it loses flexibility and cannot stretch comfortably. In each case, cracking appears when a material can no longer remain whole under the conditions imposed on it. It is the moment unity becomes too expensive. And perhaps that is why cracks feel so symbolic to us. They show the hidden history of pressure. They remind us that breaking rarely comes from nowhere. Something was pulling, drying, bending, shrinking, heating, cooling, striking, or repeating. Something found a flaw and made it important. But they also show that the path of damage is not meaningless. It follows rules. It reveals structure. It exposes the invisible map that was always inside the object. So the next time you see a crack in glass, stone, mud, wood, paint, or concrete, do not see only ruin. See a record of forces that could not be seen directly. See the line where stress gathered, where resistance failed, where energy escaped, where the material quietly explained what it had been enduring. A crack is matter becoming honest. It is the hidden map drawn on the surface at last. The strange behavior of ferrofluids. Ferrofluid looks like a liquid that has learned to grow teeth, rising into black glossy spikes the moment a magnet comes near, as if some hidden creature inside the fluid has suddenly woken up and decided to reach for the invisible. At first glance, it seems impossible because ordinary liquids do not behave like this. Water flows away from sharp points. Oil spreads into smooth skins. Ink stains, drips, and settles. But ferrofluid stands up, folds into ridges, crawls toward magnets, and forms dark metallic landscapes that look more like science fiction than a real material you could hold in a small bottle. The truth is even more interesting than the illusion. Ferrofluid is not a magical liquid metal, and it is not alive. It is usually a carrier liquid, such as oil or water, filled with extremely tiny magnetic particles, often iron oxide, so small that they remain suspended instead of sinking quickly to the bottom. Each particle is coated with a surfactant, a kind of molecular stabilizer that helps prevent the particles from clumping together permanently. Without that coating, the particles would attract, gather, and the fluid would lose its smooth behavior. With it, the particles can remain dispersed, and the liquid can flow while still responding strongly to a magnetic field. This is the first strange secret of ferrofluid. It is both liquid and magnetically responsive, because it is not one thing, but a carefully balanced mixture. The liquid gives it motion, the particles give it magnetism. The coating keeps the whole system from collapsing into a useless lump. When no magnet is nearby, the particles inside are arranged in no large visible order, jostling and drifting in the fluid. The ferrofluid may look like thick black ink, but bring a magnet close, and the particles begin to align with the magnetic influence passing through the liquid. They do not need to become a solid magnet in the ordinary sense. They simply respond together, and because there are so many of them, the whole liquid begins to act as one magnetic material that can still flow. The most famous effect is the sudden formation of spikes. These spikes are not random decorations. They appear because the liquid is caught between competing forces. The magnetic field pulls the fluid into regions where the field is stronger, encouraging it to rise and sharpen into peaks. But gravity pulls the fluid downward, and surface tension tries to keep the surface smooth and minimize its area. When the magnetic pull becomes strong enough, smoothness loses its hold. The surface breaks into a pattern of peaks, often arranged in a surprisingly regular way. This is called the Rosenzweig instability, and it is one of the most beautiful examples of a surface choosing structure under pressure. The spikes form because that shape lowers the overall energy of the system under the magnetic field. In simpler words, the fluid is finding a new balance. It is not trying to be beautiful, but balance can look beautiful when the rules are sharp enough. The spikes also tell you something important. Ferrofluid does not merely show magnetism, it changes shape because of it. A solid magnet turns, attracts, repels, or holds, but ferrofluid deforms. It becomes a moving surface where invisible influence is translated into visible architecture. This is why it feels so alive. It is not alive, but it is responsive in a way our brains associate with living things. It reacts, it reaches, it rearranges itself. It seems to sense the magnet, though there is no awareness inside it, only particles obeying physical laws. The dark spikes can also merge, stretch, collapse, and reform as the magnet moves, because the fluid is constantly seeking a balance among magnetic pull, fluid flow, surface tension, and gravity. Take the magnet away, and the spikes soften back into a smooth liquid. The creature vanishes because there was never a creature, only a condition. This makes ferrofluid a perfect reminder that form can be temporary, dependent, and real all at once. The shape exists, but only while the field demands it. There is another reason ferrofluid looks so dramatic. The particles are incredibly small, often on the scale of nanometers, which means thermal motion helps keep them from simply settling out. The liquid is filled with magnetic dust so fine that it behaves less like sand in water and more like a responsive dark mist suspended inside fluid. Because the particles are tiny and coated, they can rotate and align without the entire liquid becoming a solid clump. This is why ferrofluid can flow through cracks, coat surfaces, climb along a magnet, or gather into smooth rounded drops with spiked crowns. It is not just magnetic liquid in a crude way. It is a material engineered so that microscopic magnetism becomes macroscopic motion. And because it is engineered, ferrofluid has practical uses beyond the mesmerizing videos. One of its classic uses is in seals, especially around rotating shafts in devices where you want to keep dust, gas, or other contaminants out. A magnet can hold ferrofluid in place like a liquid O-ring, forming a seal that can remain flexible while a shaft turns. Ferrofluids have also been used in some loudspeakers, where they can sit around the voice coil, helping transfer heat away and damping unwanted motion. In medicine and research, magnetic nanoparticles related to ferrofluid concepts are studied for targeted drug delivery, magnetic imaging contrast, and controlled heating in certain cancer treatment research. Though real medical use depends on safety, control, particle chemistry, and careful testing. This matters because the visual wonder of ferrofluid is only the surface of a deeper idea. If you can make tiny particles respond to fields, you can guide matter without touching it directly. You can move, hold, seal, cool, heat, or position materials using magnetism as an invisible handle. But ferrofluid also teaches caution. It is not a toy to treat carelessly. Many ferrofluids can stain skin, fabric, and surfaces badly. Some are oil-based and messy. Some may contain materials that should not be touched, swallowed, or left around children or pets. The spikes may look like something you want to run your finger through, but the fluid is often best admired through glass or handled with proper protection. Real wonder does not require pretending something is harmless when it is not. In fact, the honesty makes it better. This strange black liquid is a carefully controlled physical system, not a fantasy substance. It behaves strangely because its ingredients and forces are carefully matched. The magnet does not command it like a mind. The field changes the energy landscape around the particles, and the fluid responds by reshaping itself. The surfactant keeps the particles apart. The carrier liquid allows motion. The nanoparticles supply magnetic response. Surface tension resists roughness. Gravity pulls downward. The spikes are the compromise. The whole event is a negotiation made visible. And maybe that is why ferrofluid feels so hypnotic. It shows that matter is not always passive. Under the right conditions, matter can become responsive, sculptural, almost expressive, without crossing into life. It can look emotional without feeling anything. It can appear intentional while obeying simple physical tendencies. A drop of ferrofluid near a magnet becomes a small theatre where the invisible becomes dramatic. Peaks rise where the pull is strongest. Valleys sink where smoothness survives, and the surface turns into a map of forces. When the magnet moves, the map changes. When the field strengthens, the spikes sharpen. When the field weakens, the liquid relaxes. You are watching a material translate an unseen environment into shape. That is the deeper lesson. We often think of shape as something fixed, carved, built, or frozen. But ferrofluid shows another kind of shape. Shape as response. Shape as conversation. Shape as the temporary answer matter gives to the forces around it. So the next time you see ferrofluid gather into black shining spikes, do not see only a strange visual trick. See a fluid filled with tiny magnetic particles, each too small to notice alone, acting together until the whole surface rises into order. See a balance between attraction and smoothness, between microscopic engineering and visible beauty. See proof that the world can hide dramatic behavior inside ordinary-looking materials, waiting for the right field to reveal it. Ferrofluid is strange not because it breaks the rules of physics, but because it follows them so clearly that the rules become visible. How heat writes secret patterns through matter. Heat is a hidden writer, and every material around you is a page where it leaves marks you may not notice until the pattern has already appeared. Touch a metal spoon left in a hot cup. Watch a pan darken unevenly on a stove. See shimmering waves rise above asphalt. Notice cracks spreading through a ceramic dish after sudden temperature change. Or look at the colored bands on heated steel. And you are seeing heat turn invisible motion into visible history. At first, heat feels simple. Something warm moves into something cold. But matter does not receive heat evenly or passively. Every material has its own way of accepting, spreading, storing, resisting, and revealing thermal energy. Metal spreads heat quickly because its internal structure allows energy to move efficiently, especially through its mobile electrons. Wood and plastic spread it much more slowly, which is why a metal handle can burn your fingers while a wooden one nearby may still feel safe. Glass can hold a temperature difference long enough to become dangerous to itself. Stone can store warmth after sunset. Water can absorb a large amount of heat before its temperature changes much, which is one reason oceans soften climate. Heat, then, is not just a number on a thermometer. It is a relationship between energy and material personality. When heat enters a solid, the atoms inside do not sit quietly. They vibrate more strongly. Those vibrations pass energy to neighboring atoms, like a crowd slowly learning a rhythm from one side to the other. In a good conductor, the rhythm spreads quickly. In a poor conductor, it spreads slowly, leaving steep differences between hot and cold regions. Those differences can write patterns. Put a cold glass under hot water too suddenly, and the outside expands faster than the inside. The outer layer wants to grow, the inner layer resists, and stress builds between them. If the stress becomes too great, the glass cracks. The crack may look like an accident, but the deeper cause is a thermal pattern. One part of the material changed size before another part could follow. This is called thermal shock, and it is why oven-safe materials are designed to tolerate temperature changes better, why laboratory glass has special properties, and why pouring boiling water into the wrong kind of glass can break it. Heat can also draw patterns through expansion. Rail tracks, bridges, sidewalks, pipes, and buildings all expand when warmed and contract when cooled. Engineers leave gaps, joints, and flexible sections because materials need room to breathe with temperature. A bridge that seems solid and unmoving is quietly changing length across day and night, summer and winter. If it were not allowed to expand, heat could turn strength into strain. Roads buckle in extreme heat. Concrete slabs lift. Metal parts warp. A sealed container may build pressure. Matter does not ignore temperature. It answers by changing shape. And when the answer is blocked, the hidden pattern becomes damage. Sometimes heat writes more gently. On a cold window, warmth and moisture from indoor air can form condensation in delicate trails, especially where the glass has tiny differences in temperature, dirt, airflow, or contact. On a heated pan, oil may thin, move, and form shimmering patterns because hotter regions change viscosity and surface tension. In a pot of soup, heat from below creates rising columns of warmer fluid and sinking regions of cooler fluid, making slow circulation that stirs without a spoon. If the conditions are right, these motions can organize into cells, repeating patches of rising and sinking flow known as convection patterns. They can appear in liquids, in the atmosphere, inside planets, and even in the sun's outer layers, though at very different scales and conditions. Heat does not simply spread. When gravity and fluid motion are involved, it can organize movement into visible structure. This is why hot air above a road shimmers. The air near the surface is warmer and less dense than the air above it, so light bends slightly as it passes through layers with different temperatures. Your eyes interpret that bending as waviness, as if the world itself is trembling. The heat is not visible directly, but its effect on air changes the path of light, turning temperature differences into distortion. A mirage is a more dramatic version of this. On a hot day, light bending through layers of air can make the road ahead look wet or reflective, not because water is there, but because the atmosphere has become a lens shaped by heat. Fire writes in even more intense ways. When a flame touches metal, the metal may change color as temperature rises. First dull red, then brighter red, orange, yellow, and, at extreme conditions, white hot. This glow is thermal radiation, matter emitting light because it is hot. But metals can also show subtler color bands after heating, especially steel, where thin oxide layers form on the surface. The thickness of those layers affects how light reflects, creating straw, blue, purple, or brownish colors that skilled metalworkers can read as clues about temperature history. The surface becomes a thermal diary. Clay and ceramics carry similar memories. A pot fired in a kiln is transformed by heat. Water is driven out. Minerals change. Particles fuse. Glazes melt and flow. Colors develop. And the soft object becomes hard and durable. The final form is not just shaped by hands. It is completed by temperature. Too little heat, and the clay remains weak. Too much, and it can slump, blister, crack, or melt. The kiln writes through chemical change, not just warmth. Food shows this in a familiar way. Bread browns, because heat triggers chemical reactions between sugars and proteins, creating new flavors, colors, and aromas. Meat sears. Coffee beans roast. Onions caramelize. A white egg turns opaque because heat changes the shape of proteins, causing them to unfold and link into a new structure. Cooking is controlled thermal transformation. You are not merely warming food, you are rewriting its chemistry. The patterns on toast, the crust of bread, the browned edge of a pancake, the darker bottom of a cookie, all are maps of where heat arrived most strongly, where moisture escaped, where reactions accelerated, and where material changed. Even living things record heat. Tree rings can be influenced by seasons and climate conditions. Coral skeletons and ice cores preserve environmental histories, including temperature-related signals, though scientists must interpret them carefully with multiple clues. Leaves wilt when heat and water stress disturb their internal balance. Skin reddens under warmth because blood vessels near the surface widen. The body sweats to cool itself through evaporation, turning heat into a survival problem solved through water. In fever, temperature shifts become part of immune response, though dangerous if too high. Heat is not just outside matter. It enters life, alters rates of reaction, changes shapes of proteins, affects membranes, and pushes living systems toward adaptation or stress. At very small scales, heat also creates motion that looks almost alive. Tiny particles suspended in fluid jitter because they are struck from all sides by moving molecules, a phenomenon known as Brownian motion. That jitter is not caused by the particles deciding where to go. It is thermal motion made visible through their restless dance. Heat writes there not as a stain or crack, but as trembling. At larger scales, heat can create gradients, and gradients are powerful because they make things happen. A temperature difference can drive a heat engine. It can power weather. It can move ocean currents. It can turn water into vapor, vapor into clouds, clouds into rain, and rain into rivers. In Earth's interior, heat helps drive slow convection in the mantle, which is connected to plate tectonics over immense time. The continents, mountains, volcanoes, and ocean basins are part of a planet still releasing internal heat from formation and radioactive decay. Heat writes not only on pans and windows, but across geological time. It lifts rock, melts minerals, fuels volcanoes, and helps reshape the crust beneath your feet. What makes all of this so quietly astonishing is that heat is often invisible until matter translates it. You cannot see thermal energy itself with ordinary eyes. You see what it does: expansion, cracking, melting, boiling, glowing, bending light, changing color, triggering chemistry, moving fluids, altering texture, softening wax, hardening clay, curling leaves, warping plastic, lifting air. Matter is the ink, heat is the hand. The pattern appears only when the material responds, and every response teaches you something about the material's nature. Metal says, "I spread heat quickly." Glass says, "I may break if you change me too fast." Water says, "I can store much before I change." Air says, "Warm me and I will rise." Food says, "Heat me and I become something else." Rock says, "Give me enough time and temperature, and I will transform." So the next time you see steam curling from a cup, color blooming on heated metal, a road shimmering in the sun, bread turning golden, or a cracked dish after sudden heat, do not see only an everyday event. See a message written by thermal energy through the hidden structure of matter. Heat is not just warmth, it is an editor of form, a mover of fluids, a maker of stress, a painter of surfaces, a driver of chemistry, and a patient force that leaves signatures wherever energy flows unevenly. The world is covered in these signatures, but most of them are so familiar that we stop reading them. Look again. An ordinary matter becomes a manuscript of temperature, each mark quietly saying, "Energy passed through here," and the material remembered. Surface tension as liquid skin. A liquid surface is not an open doorway. It is a stretched, trembling skin made by molecules holding on to one another, just tightly enough to make water behave as if it has an invisible membrane. Look closely at a drop sitting on a leaf, a glass filled slightly above the rim, a paperclip resting carefully on water, or a tiny insect walking across a pond. And you are seeing a secret boundary that most of daily life teaches you to ignore. Water seems soft because you can pour it, splash it, stir it, and fall through it. But its surface is not the same as its interior. Deep inside the liquid, each water molecule is surrounded by other water molecules pulling on it from many directions. So the forces mostly balance. At the surface, the molecules have neighbors beside and below them, but far fewer above them. That imbalance pulls the surface molecules inward and sideways, making the surface behave as though it is under tension. This is surface tension, not a solid sheet, not a real skin you can peel away, but a physical tendency of the surface to shrink, tighten, and resist being stretched. The liquid is trying, in its quiet molecular way, to expose as little surface as possible. That is why small drops tend to become round. A sphere gives a given amount of liquid the smallest possible surface area, so a falling droplet, a bead of rain on a waxy leaf, or dew on a spider web often pulls itself into curved form. Gravity can flatten larger drops, wind can distort them, and surfaces can pull them out of shape. But the underlying tendency remains. The surface wants to gather inward. This is why water can dome above the rim of a very full glass before spilling. The top does not instantly collapse because the surface molecules are pulling together, creating a delicate curved boundary that can hold slightly more than your eye expects. Add just one more drop or disturb the balance, and the dome gives way. The skin breaks not because it was fake, but because the forces were finally overwhelmed. The same idea explains why a carefully placed needle or paperclip can float on water, even though the metal itself is denser than water. It is not floating in the usual way, like wood. Instead, the object rests on the surface, bending it downward without immediately piercing it. The surface tension pulls along the curved water surface and helps support the object's weight. If you push the paperclip through, it sinks. If you place it gently, the liquid skin holds. This is the strange part. Whether something stays up or falls through can depend not only on weight, but on how gently it meets the surface. Nature often lives in that difference. Water striders, those delicate insects that skate across ponds, survive because their long legs spread their weight and are covered with tiny water-repelling hairs. Their feet press dimples into the water without breaking through. They are not walking on magic. They are walking on surface tension. Each step bends the surface like a flexible sheet, and the insect uses that deformation to stand, move, and even detect vibrations from prey or mates. To them, the water surface is not simply the top of a liquid. It is a habitat, a road, a signal board, a boundary between worlds. Beneath it, fish may swim. Above it, air moves. On it, a small creature reads the tension of molecules as landscape. Surface tension also shapes how water wets or refuses a surface. On clean glass, water tends to spread because the attraction between water and glass is strong enough to pull the liquid outward. On wax, oil-coated leaves, or many synthetic waterproof materials, water beads up because the attraction between water molecules is stronger than the attraction to the surface beneath. This is why rain forms pearls on a lotus leaf or a freshly waxed car. The drop is not choosing elegance. It is responding to competing attractions. Water holding itself together, and the surface either welcoming or resisting it. This balance gives rise to the contact angle, the angle where the liquid, solid, and air meet, though you do not need the term to feel the idea. Some surfaces invite water to spread, others make water curl inward and protect itself. A drop shape is a small negotiation between the liquid's own cohesion and the personality of the material it touches. Soap changes the negotiation dramatically. When soap or detergent enters water, its molecules gather at the surface and interfere with the way water molecules pull together. One end of a soap molecule is attracted to water, while another end avoids water and prefers oils or air. This arrangement lowers surface tension, making it easier for water to spread. Wet surfaces enter tiny gaps and lift away grease. That is why plain water may bead on oily skin or a dirty dish, but soapy water can spread and clean more effectively. Soap does not simply make water slippery, it changes the surface physics. It weakens the liquid skin. This is also why a sprinkle of pepper on water races away when soap touches the surface. The soap lowers surface tension in one region, and the stronger tension in surrounding regions pulls the surface outward, dragging the pepper with it. The pepper is not frightened, and the soap is not pushing it like a broom. The surface itself is rearranging. A difference in tension becomes motion. This effect, called the Marangoni effect, appears in many places. In tears of wine creeping up a glass and falling back in streaks, in thin film spreading unevenly, in industrial coatings, in soldering, in microfluidic devices, and even in some biological flows. Surface tension is not only a curiosity for kitchen experiments, it is part of how liquids behave whenever surfaces matter. And surfaces matter a lot when things are small. At large scales, gravity often dominates. A bucket of water spills downward. A wave crashes under its own weight. But at tiny scales, surface tension can overpower gravity. For a water droplet on a leaf, a small insect on a pond, or fluid moving through microscopic channels, the surface can become more important than the bulk. This is one reason the small world feels so different from the large one. A raindrop can cling to a window. A tiny bead of sweat can hold together on skin. A droplet can hang from a faucet, swelling slowly as gravity pulls down and surface tension holds up, until the weight becomes too great and the drop breaks free. That falling drop is the result of a contest you have watched 1,000 times without naming it. Even your own body depends on surface tension in ways that are easy to overlook. Inside the lungs, tiny air sacs called alveoli are lined with a thin layer of fluid. Surface tension in that fluid would tend to make the sacs collapse, which would make breathing extremely difficult. Your body solves this with pulmonary surfactant, a special mixture that lowers surface tension and helps keep the alveoli open. This is especially important in newborn babies, whose lungs must begin working at birth. Without enough surfactant, breathing can become dangerously hard. So the same principle that lets a water strider stand on a pond also appears deep inside the act of breathing, transformed by biology into survival. Tears also rely on surface behavior. The tear film over your eye must spread smoothly, stay stable long enough to protect and nourish the surface, and then refresh with each blink. If that film breaks up too quickly, the eye can feel dry or irritated. Again, a liquid surface is not just liquid. It is a functional boundary, a thin living interface where chemistry, comfort, and physics meet. What makes surface tension so beautiful is that it turns the edge of water into an active place. The surface is not merely where the liquid ends. It is where the liquid's internal attractions become unbalanced and visible. It is where drops take shape, insects walk, soap spreads, tears stabilize, lungs open, and tiny forces become large enough to rule the scene. We often imagine strength as something hard, rigid, and loud, but surface tension shows another kind of strength. Soft strength, quiet strength, the strength of many small attractions acting together. A single molecule cannot hold up a water strider. A whole surface can. A single pull means little. A coordinated boundary becomes a skin. So the next time you see a bead of water trembling on a leaf, or a droplet clinging to a faucet before it falls, or a small insect crossing a pond as if the surface were glass, pause before calling it simple. You are watching molecules make a boundary. You are seeing a liquid behave as though it wants to hold itself together. The surface is not solid, not permanent, not unbreakable, but for a moment it is organized enough to resist, support, curve, and shine. And in that thin, shimmering skin, the ordinary world quietly reveals one of its gentlest truths. Even softness has structure, and even water knows how to hold a shape before letting go. Capillary action and water climbing against gravity. Water does not always fall the way your eyes expect. Sometimes, when the space is narrow enough and the surface is inviting enough, it climbs upward as if gravity has briefly lost the argument. You can see it in the corner of a paper towel touching a spill, in ink creeping through paper, in a thin glass tube dipped into water, in a candle wick pulling melted wax toward a flame, in soil drawing moisture through tiny gaps, and in the delicate veins of a leaf, quietly supplied from below. At first it feels almost wrong. Water is heavy, it should run downward, gather in low places, obey the pull of earth like everything else. But capillary action reveals that gravity is not the only voice in the conversation. At small scales, other forces become powerful enough to compete with it. The key is the relationship between the liquid and the surface it touches. Water molecules are attracted to each other, but they can also be attracted to other materials, such as glass, paper fibers, plant cell walls, or tiny mineral surfaces in soil. When water is more attracted to the surrounding surface than it is pulled back into itself, it begins to wet that surface. In a very narrow tube, the water at the edges climbs along the walls because of this attraction. The rest of the water follows because water molecules hold on to one another. So the climb is a partnership. Adhesion pulls water toward the surface, and cohesion helps the water column stay connected. The narrower the space, the more important the surface becomes compared with the weight of the water. In a wide drinking glass, water does not climb the walls very far because there is too much volume and gravity dominates. But in a hair-thin tube, a paper fiber, a crack in dry soil, or the microscopic channels inside a plant, the surface influence becomes strong. The water curves upward along the edges, forming a meniscus, that familiar curved surface you may have seen in a measuring tube. In glass, water usually curves downward in the middle because it climbs slightly at the sides, showing its attraction to the glass. That small curve is a clue that the liquid is not merely sitting there, it is interacting with the container. Capillary action is what happens when this edge behavior becomes strong enough to pull liquid into a narrow space. A paper towel is one of the easiest ways to watch it. Touch the corner to a drop of water, and the wet region spreads upward and outward, even if you hold the towel above the spill. The towel is full of tiny spaces between fibers, a hidden forest of microscopic channels. Water attaches to the fibers and pulls itself along them, while more water follows behind. The motion slows over time because gravity, evaporation, and the limits of the available channels begin to matter. But the initial rise can be surprisingly fast. This is why towels absorb, why tissues draw tears, why cloth wicks moisture, and why ink can feather through cheap paper. The liquid is not choosing a path. It is exploring the tiny geometry of the material, filling the spaces where attraction and narrowness allow it to move. A candle wick works through the same principle. The flame melts wax near the top, and capillary action pulls liquid wax upward through the fibers of the wick. The wax vaporizes near the flame and burns, while more wax is drawn upward to replace it. Without that hidden upward feeding, the flame would quickly run out of fuel at the burning tip. A candle, therefore, is not just a small fire sitting on wax. It is a capillary system, a quiet pump with no moving parts, lifting fuel toward heat through the architecture of woven fibers. Plants use a much more complex version of upward water transport. Water can rise through narrow spaces in plant tissues, partly because of capillary action, but this alone cannot explain how tall trees lift water all the way to their highest leaves. That is where the honest science becomes more interesting. In plants, capillary effects help, but the main lifting force in tall plants comes from transpiration. Water evaporating from leaves creates tension that pulls a continuous column of water upward through xylem vessels. Helped by cohesion between water molecules and adhesion to the vessel walls, root pressure can also contribute in some conditions. So plants are not simply sucking water up like a straw by capillary action alone. They are using a linked system. Tiny tubes, molecular attraction, evaporation, pressure differences, and living structure all working together. A tree is, in a sense, a vertical water machine powered partly by sunlight warming leaves and drawing water into the air. Each leaf becomes a small place where water leaves the plant, and that loss helps pull more water from the roots. The quiet upward movement inside a tree is one of the most elegant examples of physics serving life, without any need for motors or pumps in the way humans build them. Soil also depends on capillary action. After rain, water does not simply sink straight downward and disappear. Some of it is held in tiny spaces between soil grains. Fine soils with very small pores can pull water upward or hold it tightly, while sandy soils with larger gaps drain more easily. This is why soil texture matters so much for plants and agriculture. Too much drainage and roots may dry out. Too much water held too tightly, and air spaces disappear, suffocating roots. Capillary movement helps distribute moisture through the ground, but it also explains why dampness can creep upward through porous building materials. In old walls, bricks, concrete, or stone can draw groundwater upward through tiny pores if there is no proper barrier, leaving stains, salts, peeling paint, and damage over time. Water climbing against gravity can nourish a plant, but it can also slowly invade a building. The same physics becomes helpful or harmful depending on where it happens. Capillary action also allows scientists to separate mixtures in simple but powerful ways. In paper chromatography, a small spot of ink or plant pigment is placed near the bottom of a strip of paper, and a solvent climbs upward through the paper by capillary action. As it rises, different chemicals travel at different speeds because they interact differently with the paper and the solvent. What began as one dark spot can separate into bands of color. The climbing liquid becomes a quiet investigator, revealing that a single-looking substance may be made of many hidden parts. This is another beautiful lesson from capillary action. Movement through small spaces can sort the world. It can absorb, feed, stain, clean, transport, reveal, and sometimes damage. It turns narrowness into power. At human scale, gravity feels dominant because we live among large objects. Cups, rivers, rain, waves, buckets, bodies. But in the small spaces of fibers, pores, tubes, cracks, and cells, the balance changes. Surface forces become large compared with weight. The world of the tiny has different priorities. A droplet can cling, a liquid can crawl, a wick can feed a flame, a root can draw from damp soil, a strip of paper can lift color upward. And perhaps that is why capillary action feels so quietly magical, even when you know the science. It shows that climbing does not always require effort in the way we imagine. Sometimes a path is so narrow and an attraction so persistent that liquid rises because the material itself invites it upward. So the next time you watch a paper towel drink a spill, or see water darken the edge of dry soil, or notice ink spreading through paper like a small blue vein, pause before calling it ordinary. You are seeing gravity being challenged not by strength, but by intimacy. Water climbs because it is close enough to touch the walls that guide it, close enough for molecular attraction to matter more than the downward pull trying to stop it. In that tiny upward movement, the world reveals a softer kind of power. Not the power to overcome gravity by force, but the power to slip through small openings, hold together, and rise by connection. Static electricity in ordinary objects, a plastic comb, a wool sweater, a balloon, a strip of tape, and a dusty television screen can all become tiny electrical worlds, quietly storing imbalance until the invisible charge around them begins to pull, cling, lift, or spark. Static electricity feels like a small household trick because it appears in harmless little moments. Socks crackling in the dryer, hair rising after a balloon rubs against it. Plastic wrap grabbing a bowl, dust gathering on screens, a sweater snapping in the dark as you pull it over your head. But behind these ordinary annoyances is a deep rule of matter. Objects are not always electrically neutral in practice, even if they begin that way. Atoms contain positive and negative charges, and most everyday objects usually balance them so well that you notice nothing. But when two materials touch and separate, especially if they rub across each other, some electrons can move from one surface to the other. One object ends up with a little extra negative charge. The other is left slightly positive. This is often called the triboelectric effect. Though the name sounds more complicated than the idea, it simply means that contact between different materials can separate charge. Rubber, plastic, wool, glass, human hair, paper, silk, and many synthetic fabrics do not all hold electrons with the same ease. Some tend to give them up more readily, while others tend to hold them more strongly. So when they meet, press, slide, and part, they may leave with an electrical memory of that contact. The strange part is that the charge can remain for a while, especially on insulating materials. A conductor, like metal, allows charge to move around easily, so extra charge can often spread out or escape if there is a path. An insulator, like plastic, rubber, dry cloth, or glass, does not let charge move freely, so separated charge can sit in place, trapped on the surface like invisible dust. This is why static electricity is so common with plastics and fabrics. They do not simply let the imbalance flow away. They hold it. A balloon rubbed on hair becomes charged and can stick to a wall, not because the wall is charged in the same way, but because the balloon's electric field shifts charges slightly inside the wall's surface. The wall remains overall neutral, but the charges within it are rearranged just enough that the side closer to the balloon is attracted. This is called polarization, and it is one of the most important hidden behaviors in static electricity. A charged object can attract a neutral object by gently separating its internal charges. That is why tiny bits of paper leap toward a charged comb. The paper pieces are not tiny magnets. and they do not need to start charged. The comb's electric field rearranges charge within them, making the nearer side more attracted than the farther side is repelled. For a moment, the paper becomes a follower of an invisible field. This same principle helps explain why dust clings to screens, shelves, plastic surfaces, and electronics. Dust particles can become charged, or they can be attracted by charged surfaces through polarization. A television or computer screen, especially older display types, can build up electrostatic effects that pull dust from the air. Plastic objects often do the same after being wiped with a dry cloth. Cleaning can sometimes make static worse because rubbing adds charge, and then the newly charged surface attracts more dust. This is one reason anti-static sprays and special cloths exist. They help charge leak away more easily or reduce charge buildup. Static electricity is not only about sparks. Often it is about attraction so small and patient that it collects a visible layer over time. In laundry, the story becomes a storm of fabrics. Inside a dryer, clothes tumble, touch, separate, and rub again and again while warm, dry air removes moisture. Synthetic fabrics can build charge especially well, and because the air is dry, the charge does not leak away easily. Oppositely charged garments attract, causing static cling. Socks attach to shirts, shirts grip your body, and thin fabrics fold into one another as if they have become strangely affectionate. Dryer sheets work partly by coating fabrics with compounds that make surfaces slightly more conductive or reduce friction, allowing charge to dissipate more easily. Humidity also changes everything. On a humid day, a thin layer of water molecules can gather on surfaces, giving charge more ways to move and fade. On a dry winter day, surfaces stay more insulating, so static builds and lingers. This is why the same carpet, same sweater, and same shoes may produce shocks in January, but not in a damp summer. The objects have not become magical. The air has changed how easily charge can escape. Static electricity can also be useful. Photocopiers and laser printers rely on controlled electrostatic attraction. A drum inside the machine is given a pattern of electric charge using light, and toner powder sticks to the charged regions before being transferred to paper and fused with heat. Every printed page is, in a hidden way, a static electricity sculpture made practical. Electrostatic painting uses charged paint droplets attracted to an object, helping create more even coating and reducing waste. Some air purifiers use electrostatic principles to charge particles and collect them on plates, though real performance depends on design, maintenance, and safety. Powder coating, industrial separation, and some manufacturing processes also use charged particles because electricity can guide small pieces of matter more delicately than gravity or airflow alone. Static electricity, then, is not merely a nuisance that makes your hair stand up. It is a tool for moving tiny things without touching them directly. But it also has dangers when scaled into the wrong environment. A spark that is harmless in your living room can become serious near flammable vapors, fuel, or fine combustible dust. In places where gasoline fumes, solvent vapors, grain dust, coal dust, or powdered materials are present, static discharge can ignite a fire or explosion if conditions are right. This is why fuel trucks, aircraft, factories, and grain handling systems use grounding, bonding, humidity control, and anti-static measures. Grounding gives charge a safe path to leave before it builds enough to spark. Bonding connects objects together so they do not develop a dangerous voltage difference between them. The lesson is simple but important. Static electricity is small only when the stored energy and environment are small. The same basic principle, charge imbalance seeking release, can be a toy, a tool, or a hazard depending on the scale and setting. One of the most dramatic classroom demonstrations is the Van de Graaff generator, a machine that uses a moving belt to build up charge on a metal dome. Touch it while standing insulated from the ground, and your hair may rise because each strand gains similar charge and repels the others. The hair spreads apart, not because it is frightened or filled with energy like a battery, but because like charges push away from one another. The body and hair become part of one charge system. It looks funny, but it reveals a serious truth. Charge can organize matter through attraction and repulsion without any visible connector. The invisible becomes visible only because something light enough, like hair, paper, dust, or powder, responds. This is the heart of static electricity in ordinary objects. It is not the flow of current through wires doing work continuously. It is stored imbalance. It is separated charge waiting on a surface. It is tension without motion until a path appears. Sometimes the path is a doorknob and the result is a snap. Sometimes the path is dust drifting toward a screen. Sometimes the path is toner powder forming letters. Sometimes it is a balloon clinging to a wall long after the rubbing stopped. And perhaps that is why static electricity feels so strangely personal. It hides in objects you trust to be simple. A sweater becomes an electrical surface. A comb becomes a field source. A piece of tape peeled from a roll can attracts scraps like a tiny spell. A plastic wrapper can cling to your hand as if it wants to stay. These things are not alive, but they behave as if they have preferences because charge gives them invisible relationships. Attraction and repulsion appear where you expected only touch and separation. So the next time ordinary objects crackle, cling, jump, or gather dust, do not dismiss the moment as a meaningless inconvenience. You are seeing matter remember contact. You are seeing electrons shifted by ordinary friction. You are seeing neutral objects pulled by polarization, dry air preserving imbalance, and surfaces becoming quiet reservoirs of charge. Static electricity is the small domestic face of a vast physical rule. The world is full of invisible tensions, and even the simplest object can briefly become a map of forces you cannot see until something light enough begins to move. The physics of hair. Standing up. Hair stands up because each strand is more than a decoration on your body. It is a tiny flexible fiber rooted in skin, sensitive to charge, moisture, motion, temperature, and even emotion, waiting for the right physical or biological signal to turn softness into a visible warning. You may notice it after rubbing a balloon on your head, after pulling off a winter hat, during a dry day when your hair lifts away from your scalp, or in a completely different way when cold air or fear gives you goosebumps and the fine hairs on your skin rise. These moments look similar from the outside, but they do not all come from the same cause. Sometimes hair rises because of electricity. Sometimes it rises because of tiny muscles in the skin. Sometimes it spreads because each strand has become too similar to its neighbors and begins to push away. The first kind, the familiar floating hair after friction, happens because hair can gain or lose electrons when it rubs against another material, such as a balloon, a plastic comb, a wool hat, or a synthetic fabric. Once many strands carry the same kind of electric charge, they repel one another. Each hair is light, thin, and flexible, so even a small repulsive force can lift it away from nearby strands. If the hair were heavy like wire, the effect would be harder to see. If it were fixed firmly along its whole length, it could not spread. But hair is anchored only at the root and free along most of its length, so charge turns it into a tiny movable needle. Each strand tries to get farther from the others, and the result is that familiar halo of lifted hair, as if your head has become surrounded by invisible tension. The hair is not reaching upward because it wants the sky. It is spreading outward because like charges repel, and upward is simply one of the directions available when the strands are attached at one end. Gravity still pulls them down. Stiffness resists bending, and air slows the motion. But when the electrical repulsion is strong enough compared with the hair's weight and flexibility, the strands rise. This is why fine dry hair often responds more dramatically than heavy wet hair. Water changes the whole story. Moisture on hair and in the air helps charge leak away more easily, and wet hair is heavier and more likely to clump together because water creates contact between strands. On dry winter days, charge remains trapped longer, and the air offers fewer pathways for it to dissipate. That is why hats, scarves, plastic combs, and dry indoor heating can make hair stand up more often. Conditioner and hair oils can reduce the effect partly by smoothing the hair surface, adding moisture, and making strands less likely to build and hold charge in the same way. Hair texture matters too. Straight hair, curly hair, thick hair, fine hair, damaged hair, and freshly washed hair can all respond differently. because shape, surface roughness, natural oils, and moisture content change how strands rub, cling, separate, and bend. A single hair also has structure. Its outer layer, called the cuticle, is made of overlapping microscopic scales. When hair is dry or damaged, the cuticle can become rougher, increasing friction between strands and making charge buildup and frizz more likely. What you call bad hair on a dry day is often a visible conflict between fiber structure, moisture, charge, and air. But not every raised hair is caused by electricity. Goosebumps come from a biological reflex. At the base of many hairs are tiny muscles called erector pili. When you are cold, frightened, emotionally moved, or sometimes even when music gives you chills, your nervous system can trigger these muscles to contract. The skin puckers and the hair is pulled more upright. In furry animals, this response can trap more insulating air near the body when it is cold, or make the animal look larger when threatened. In humans, with much less body hair, the effect is mostly a leftover from our evolutionary past, still attached to our nervous system, even though it no longer keeps us warm in any major way. That is why a scary sound, a sudden memory, a beautiful song, or cold air across your arms can produce the same tiny rising hairs. Your body is not confused exactly. It is using an old physical strategy with a modern emotional range. The skin becomes a field of small raised points, each one marking a contraction too small to matter alone, but visible when many happen together. This is different from charged hair spreading outward, but both reveal the same principle in different languages. Hair makes invisible forces visible. Electricity lifts through repulsion, emotion and cold lift through muscle. In both cases, something hidden inside or around you becomes a shape on the surface. There is also a serious side to hair standing up that belongs to storms and safety. If you are outdoors during a thunderstorm and your hair suddenly stands on end, or you feel tingling on your skin, that can be a dangerous sign that a strong electric field is present, and lightning may be about to strike nearby. It does not mean lightning is guaranteed to hit you, and it is not something to test or admire. It means you should immediately get to a safer place if possible, away from open fields, isolated trees, high points, water, and metal structures, following proper lightning safety guidance. In that situation, hair becomes an alarm, not a curiosity. A strong electric field can polarize and charge objects, including your body and hair, and the strands respond before the main discharge occurs. The same basic repulsion that makes hair rise in a classroom demonstration can become a warning in the atmosphere, where the scale is no longer playful. This is one of the strange things about physics. The same principle can appear as a party trick, a beauty problem, a biological reflex, or a life-threatening signal depending on the amount of energy involved. Even in ordinary life, the raised hair teaches you about balance. For a strand to stand, several forces must be compared. The electric push between charged strands, the pull of gravity, the stiffness of the hair shaft, the anchoring at the follicle, the drag of air, and the dampening effect of moisture and oils. Your hair is therefore a physical sensor that reacts differently from day to day because the world around it has changed. The same comb may do little in humid weather and create a floating crown in dry air. The same sweater may cling on one day and behave normally on another. The same emotional scene may leave one person covered in goosebumps and another person still, because nervous systems vary. Hair looks simple because it is thin, familiar, and silent, but it sits at the meeting point of materials science, electricity, biology, weather, and emotion. It can tell you about the dryness of a room, the roughness of a fiber, the charge left behind by friction, the state of your nervous system, or the danger of a charged sky. And perhaps that is why the image of standing hair feels so memorable. It turns the unseen into something almost comic, almost eerie, almost alive. A force too small to notice directly spreads through strands, and suddenly your body has a visible aura. A feeling too deep or sudden for words contracts tiny muscles, and your skin answers before your voice does. A storm builds charge above you, and the hairs on your head may respond before thunder arrives. So the next time your hair lifts after a hat, spreads around a balloon, frizzes in dry air, or rises during a chill, do not see it as a meaningless little oddity. See each strand as a fine instrument, light enough to move when hidden forces speak. Hair stands up because the world is touching it through charge, climate, muscle, and memory. And for a brief moment, your body lets you see what is usually invisible. The secret structure of foam. Foam is what happens when emptiness learns how to hold a shape. At first it seems too light to matter. A crown of bubbles on coffee, white surf on a beach, shaving cream in your palm, soap foam in a sink, the airy crumb inside bread, the soft padding in a mattress, the pale head on a glass of beer. It looks like almost nothing, a temporary mess of air and liquid, something that collapses if you wait long enough. But foam is not just bubbles gathered together. It is a hidden architecture, a crowded city of gas pockets separated by thin walls, where every wall is pulled, drained, stretched, squeezed, and slowly rearranged by physical forces. A single bubble is simple enough to admire, but foam is more complicated because each bubble must share space with many neighbors. It cannot stay perfectly round because round bubbles packed together leave gaps, and foam is a system under pressure to use its space efficiently. So the bubbles press against one another, flatten at their borders, and become many-sided cells. If you look closely at dry foam, the kind with lots of gas and very little liquid between bubbles, you may see shapes that look almost like tiny polygons, each cell adjusted by the cells around it. The foam is soft, but its structure is not careless. Each film between bubbles pulls tight. Each junction forms where several films meet. Each cell is trapped inside a network that is constantly trying to reduce surface energy, while also obeying the pressure differences between neighboring bubbles. This is why foam can behave in a way that feels almost contradictory. It can flow like a liquid when you stir it, but it can also stand like a soft solid when left alone. Shaving cream holds peaks. Whipped cream can sit on a spoon. Sea foam can pile on shore. A cluster of bubbles can wobble and resist, then suddenly slide and rearrange. Foam is not purely liquid, not purely gas, and not truly solid. It is a material made from boundaries. Its strength comes from the thin films and the way those films lock the bubbles into a shared structure. The liquid drains downward through the network under gravity, leaving thinner films above and wetter regions below. This drainage changes the foam over time. A fresh foam may be glossy and stable, but slowly, liquid slips away. Films become thinner, bubbles become more fragile, and the whole structure begins to age. Some bubbles pop, others merge. Larger bubbles grow at the expense of smaller ones because gas pressure is usually higher inside small bubbles, so gas can diffuse from smaller bubbles into larger ones through the films. This process, called coarsening, makes foam become rougher and less uniform as time passes. You can see it in old soap foam, in the changing head of a drink, in bubbles that begin fine and creamy but slowly become larger, weaker, and easier to break. Foam has a lifespan, and its secret structure is always fighting collapse. To make foam last, you need stabilizers. Soap helps because its molecules gather at the air-water surface and make films more flexible. Proteins can stabilize food foams, which is why egg whites can be whipped into meringue, and cream can be whipped into a light structure that holds air. In beer, foam depends on proteins from malt, compounds from hops, carbonation, glass cleanliness, and the way bubbles rise and collect at the surface. In bread, foam begins in dough as yeast produces carbon dioxide, and gluten helps trap the gas in elastic pockets. Later, heat sets the structure, turning a temporary foam into a permanent airy solid. A sponge, a foam cushion, a marshmallow, and a loaf of bread all carry the same deeper idea in different forms. Gas divided into many small compartments, held by walls strong enough to keep the structure from becoming one empty space. The size of the bubbles matters. Tiny bubbles can make a foam feel smooth, creamy, and dense, while large bubbles make it feel coarse and fragile. This is why the texture of whipped cream, cappuccino foam, ice cream, bread, and cake depends so much on how air is introduced and stabilized. In ice cream, small air bubbles and tiny ice crystals help create smoothness. If the structure becomes coarse, the dessert feels icy or foamy in the wrong way. In a cake, beaten batter traps air, and baking expands gases, while proteins and starches set around them. The final softness is architecture you can eat. It is not only flavor, it is physics held between your teeth. Foam also plays serious roles outside the kitchen. Firefighting foams can spread over burning liquids to separate fuel from oxygen and suppress vapor, though some older types have raised environmental concerns because of persistent chemicals, so modern use and regulation require care. Metal foams and ceramic foams can be engineered to be light but strong, useful in energy absorption, filtration, insulation, and structural design. Packaging foam protects fragile objects because its many cells deform and absorb impact. A bicycle helmet or protective padding often works by allowing a foam structure to crush in a controlled way, turning dangerous, sudden energy into deformation across many tiny cells. The foam sacrifices its structure so your body does not have to. That is one of the most beautiful and practical things about foam. Weakness distributed carefully can become protection. A single thin wall is fragile, but millions of thin walls arranged together can cushion, insulate, float, filter, and support. Nature uses foam-like structures too. Bone is not a solid block. Inside many bones is a porous, foam-like architecture called trabecular bone, arranged to provide strength while reducing weight. Some plant tissues contain air spaces. Pumice, a volcanic rock, forms when gas bubbles are trapped in cooling lava, leaving it so porous that some pieces can float on water. Seafoam forms when waves churn seawater containing dissolved organic matter, salts, and tiny particles, stabilizing bubbles long enough to gather into pale, drifting masses. It can look pure and soft, but it is the ocean's chemistry and motion made visible. Foam therefore teaches that structure does not always require heaviness. Sometimes structure comes from separating emptiness into cells. The air inside foam is not useless. It is the reason foam can be light, insulating, compressible, and soft. The walls matter, but so do the voids. Remove the gas and foam becomes a puddle, a paste, a solid lump, or a collapsed residue. Remove the walls and it becomes loose air. Foam exists only because emptiness and boundary cooperate, and perhaps that is why it feels so quietly philosophical. It shows that something can be mostly air and still have form. Something can be temporary and still be engineered. Something can be fragile in each small part and useful as a whole. The foam in your sink may vanish in minutes, but while it lives, it is a small lesson in materials science, films pulling tight, bubbles sharing walls, liquid draining, gas diffusing, cells rearranging, structure aging. It is a world made from surfaces under tension and spaces under pressure. So the next time you see foam gathering at the edge of a wave, sitting on coffee, rising in bread, cushioning a package, or trembling in your hand as shaving cream, do not dismiss it as empty fluff. Look at it as a secret architecture of trapped air, a delicate network where boundaries do the work of walls and tiny cells turn nothingness into a material. Foam is not the absence of substance. It is substance stretched around absence, and for a little while, that is enough to hold a shape. Brownian motion and the jitter of molecules. A pollen grain trembling under a microscope once helped prove that the invisible world is not still, because its tiny restless dance revealed that matter is being struck from all sides by molecules too small for the eye to see. In 1827, the botanist Robert Brown was studying small particles from pollen suspended in water when he noticed something strange. They jittered constantly, moving in irregular little paths, even though they were not alive, not swimming, not trying to go anywhere. At first, this motion could have looked like some mysterious life force hidden inside the particles, but Brown tested other materials too, including dust from inorganic matter, and saw the same kind of movement. The trembling was not caused by the pollen being alive. Something else was happening. The water, which looked calm to the human eye, was not calm at all. It was full of molecules moving rapidly in every direction, colliding with the suspended particle again and again. Most of those impacts balanced out because hits came from all sides, but not perfectly. At one moment, a few more molecules struck from the left than the right, nudging the particle to the right. A moment later, more struck from below than above, nudging it upward. The particle's visible jitter was the large-scale trace of countless invisible collisions. It was like watching a boat shake on a dark ocean, unable to see the waves clearly, but knowing they must be there because the boat will not stop moving. This is Brownian motion, the irregular movement of tiny particles suspended in a fluid caused by the ceaseless thermal motion of molecules around them. The smaller the particle, the easier it is for molecular impacts to move it noticeably. A large grain of sand in water is too heavy and too massive for these tiny hits to make it dance in a visible way. But a microscopic speck is light enough to be pushed around by the unevenness of the molecular crowd. Temperature matters too. Warmer fluids contain faster moving molecules, so the jitter tends to become more energetic. Viscosity matters as well. In a thicker liquid, motion is more strongly resisted, so the particle wanders more slowly. Particle size, fluid thickness, and temperature all shape the dance. This is why Brownian motion is not just random shaking. It is a measurable window into the hidden activity of matter. In the early 20th century, Albert Einstein gave a mathematical explanation of Brownian motion, showing how the visible wandering of small particles could be connected to the size and behavior of molecules. Jean Perrin later performed careful experiments that supported these ideas and helped convince many scientists that atoms and molecules were not just useful theories, but real physical entities. That is the remarkable part. A tiny speck drifting under a microscope became evidence for the atomic nature of matter. The jittering particle was not important because of what it was, but because of what was pushing it. It made the unseen believable. It turned the idea of molecules from a hidden explanation into something indirectly visible. You could not see the water molecules themselves, but you could see their fingerprints in the motion of the particle. This is one of science's most beautiful habits. It often proves the invisible by watching what the invisible does to something visible. Brownian motion also helps explain why small particles spread through liquids and gases. A speck does not travel in a straight, purposeful line. It wanders, turns, pauses, reverses, and wanders again. But when many particles do this, they gradually spread out from crowded regions into less crowded ones. That spreading is part of diffusion. The reason a drop of dye slowly disperses in water. The reason tiny particles in air do not stay perfectly arranged. And the reason many processes in cells depend on molecular wandering. Inside living cells, Brownian motion is not a nuisance. It is part of the environment. Molecules bump, drift, collide, and sometimes meet the partners they need for chemical reactions. A protein does not always march directly to its destination like a person walking down a road. At small scales, life is full of wandering searches, random encounters, and shapes that only work because motion never stops. Cells have ways to organize and guide this chaos, using membranes, channels, motors, and chemical signals, but the underlying jitter remains. The small world is not quiet machinery. It is more like a crowded room where everything is jostling, and life has learned how to do delicate work inside that crowd. Brownian motion is also important in materials like milk, paint, ink, fog, and many medicines, where tiny particles remain suspended instead of instantly settling. Such mixtures are called colloids, and their stability often depends on a balance of particle size, fluid motion, surface chemistry, electrical effects, and gravity. If particles are small enough, Brownian motion helps keep them stirred at the microscopic level, resisting simple settling. This is why the texture of paint, the smoothness of certain foods, the behavior of aerosols, and the delivery of some nanoparticles in research can all involve the same restless principle. But Brownian motion does not mean tiny particles are magically free from gravity forever. Larger particles settle more easily. Particles can clump, fluids can dry, surfaces can attract. Real systems are full of competing effects. The lesson is not that randomness solves everything, but that at small scales, random molecular motion becomes a force you must take seriously. It can move, mix, blur, stabilize, disturb, and reveal. What makes Brownian motion so quietly powerful is that it changes your sense of stillness. A glass of water on a table looks peaceful. A beam of light in a room looks empty unless dust crosses it. A cell under a microscope may seem like a tiny orderly structure, but underneath, molecules are always moving. Not because something is broken, not because there is wind inside the water, not because life is secretly pulling every particle, but because temperature itself is motion at the molecular scale. To be warm at all is to contain restless movement. Absolute stillness would mean a world far stranger and colder than the one we live in. So the next time you see a tiny particle drift in water, or dust tremble in air, or dye slowly spread through a cup, imagine the hidden storm beneath the calm surface. The visible speck is only the messenger. Around it, molecules are striking, retreating, returning, colliding, and changing direction in numbers beyond ordinary imagination. Brownian motion reminds you that the smallest visible movements can carry enormous meaning. A jittering grain once helped humanity believe in atoms. A wandering speck became a doorway into the molecular world. And in that restless little dance, matter confessed one of its deepest truths. Even when the world appears still, it is trembling with invisible lifelike motion, not because it is alive, but because it is made of things that never stop moving. How friction creates heat from motion. Rub your hands together on a cold day, and you are performing one of the oldest transformations in the universe, turning organized motion into heat. At first it feels ordinary, almost too simple to notice. Your palms slide, your skin resists, warmth appears, and the body accepts the result without asking where the heat came from. But that small comfort hides a deep physical truth. Friction is not just a force that slows things down. It is a doorway through which motion becomes microscopic disorder. When two surfaces move against each other, even surfaces that look smooth, they are not truly smooth at the scale where atoms and molecules meet. They are covered in tiny hills, valleys, ridges, bumps, scratches, and contact points. Under a microscope, a polished table, a metal blade, a stone floor, or your own skin would look far rougher than your fingers suggest. When one surface slides over another, these microscopic high points catch, bend, break, deform, and release. Some parts stick for a moment, then slip. Some tiny structures are torn or rearranged. Some energy that once belonged to the large motion of your hand is passed into the tiny vibrations of atoms and molecules inside the materials. And that is heat. Not a mysterious substance being created from nowhere, but motion becoming smaller, more scattered, more disorganized. Your hands move in one clear direction, but after friction does its work, much of that energy has been spread into countless tiny motions inside the skin. The warmth you feel is the body sensing that microscopic agitation. This is why friction is often called a dissipative process. It takes energy that is organized enough to do visible work and disperses it into thermal energy that is harder to gather back into the same clean motion. A sliding book stops because its motion is not destroyed. It is transformed into tiny vibrations and slight heating in the book, the table, and the surrounding air. A car's brakes work because brake pads press against rotating discs or drums, converting the car's kinetic energy into heat. That heat must go somewhere, which is why brakes can become dangerously hot on long downhill roads if they are overused. The vehicle slows, not because the energy vanishes, but because the energy of motion is poured into the materials as heat. Tires warm as they roll because rubber deforms against the road, and internal friction inside the tire converts some motion into warmth. Drill bits heat up as they cut, saw blades warm as they bite through wood. A rope sliding quickly through your hands can burn skin because friction concentrates energy into a small area faster than the body can carry it away. Even a match works through this principle. When you strike it against a rough surface, friction creates local heating, and that heat helps trigger chemical reactions in the match head. The flame seems sudden, but the first step is motion being concentrated into a tiny hot region. Fire by friction, used in ancient methods of starting flames, depends on the same idea. Repeated rubbing or drilling heats dry material until it can smolder. What makes this so interesting is that friction is both useful and wasteful, depending on what you want. Without friction, walking would be almost impossible. Your foot pushes backward against the ground, and friction allows the ground to push you forward. Without enough grip, your foot slips, and your intended motion becomes uncontrolled sliding. Friction lets tires hold roads, nails stay in wood, knots hold rope, pencils leave marks, screws fasten materials, and your hand grasp a cup. But the same friction that gives control also steals energy. Machines wear down because surfaces rub, engines heat. Gears need lubrication. Bearings are designed to reduce unwanted friction by replacing sliding with rolling, or by separating surfaces with thin films of oil. Lubricants do not make friction disappear completely, but they reduce direct surface contact, allowing parts to move more smoothly and carry heat away. This is why oil matters inside engines, why grease matters in hinges and machinery, and why a dry bicycle chain becomes noisy, inefficient, and prone to wear. Friction is not one single simple thing either. There is static friction, which resists the start of motion, and kinetic friction, which acts when surfaces are already sliding. Static friction is why a heavy box can sit on a floor while you push gently and nothing happens. The microscopic contact points between box and floor are resisting the beginning of sliding. Push harder, and once your force overcomes that resistance, the box starts to move. Often it becomes easier to keep it moving than to start it, because kinetic friction can be lower than static friction. That is why the first shove feels hardest. There is also rolling resistance, where an object like a wheel loses energy because it and the surface beneath it deform slightly as it rolls. A steel train wheel on a steel rail has relatively low rolling resistance, which is one reason trains can move heavy loads efficiently. A soft tire on a rough road loses more energy through deformation, grip, and heat. At the smallest level, friction can involve adhesion between molecules, roughness between surfaces, deformation of materials, and even tiny chemical changes. It is not merely rough things scraping. Smooth things can also have friction because atoms can attract and resist separation. Very clean, very smooth metal surfaces in a vacuum can even stick together strongly because there is no thin layer of air, oxide, oil, or dirt keeping them apart. This shows that friction is partly about contact, and contact is more complicated than it looks. The surfaces in your everyday world are usually covered with films of moisture, oils, dust, oxides, and microscopic debris, all of which influence how they slide. Your skin grips glass differently when dry, wet, oily, or dusty. Shoes grip floors differently depending on rubber softness, floor texture, water, sand, and pressure. A road after rain can become slippery, not just because water is smooth, but because water separates tire from road, fills tiny surface gaps, and can reduce the contact needed for grip. In extreme cases, a tire can ride on a film of water and lose contact almost completely. So friction is not a fixed property of an object alone. It is a relationship between two surfaces and the conditions between them. Heat from friction also changes the relationship while it happens. As surfaces warm, materials can soften, expand, dry out, melt slightly, or change chemically. This can increase or decrease friction depending on the situation. Rubber tires become warmer and more flexible, which can improve grip up to a point, but too much heat damages them. Metal parts can expand and seize if lubrication fails. A fast-moving spacecraft or meteor does not heat only because of simple rubbing in the everyday sense. Much of the heating comes from compressing air violently in front of it. But the broader lesson remains that motion through a resisting medium can transform enormous kinetic energy into heat. When a meteor streaks through the atmosphere, the glowing trail is a dramatic sign that fast motion and resistance have turned the sky itself into a furnace around it. On a gentler scale, when you stir a thick liquid, internal friction within the fluid, called viscosity, also converts motion into heat, though the temperature rise may be too small to notice. Honey resists stirring more than water because its internal layers slide past one another with more difficulty. That resistance is friction inside a fluid. A reminder that friction is not only between dry solids. It can happen wherever motion is resisted, and organized movement is scattered into smaller molecular motion. This is one reason the universe has a direction we feel so deeply in everyday life. You can rub your hands together and make heat, but you cannot easily gather the random warmth from your hands and turn it back into the exact rubbing motion without machinery and losses. Energy is conserved, but its usefulness changes. Friction turns neat motion into a warmer, more spread out form. It is one of the ways the world forgets precise movement and remembers only heat. And maybe that is why friction feels so ordinary and yet so profound. It is the reason you can walk, write, hold, break, carve, polish, light a match, and warm your hands. It is also the reason machines wear, motion fades, surfaces age, and energy must constantly be supplied to keep things moving. Friction is both helper and thief, grip and loss, control and decay. It lets your body interact with the world, but it also reminds every moving thing that movement has a cost. So the next time your palms warm as you rub them together, or your brakes smell hot after a steep road, or a rope burns your skin, or a match flashes into flame, do not think of heat as appearing from nowhere. Think of motion being broken into countless tiny motions too small to see. Think of surfaces catching, slipping, deforming, vibrating, and passing energy inward. Friction creates heat because the visible world is constantly being translated into the microscopic world, and every time motion is resisted, some of its order is scattered into warmth. That warmth is the memory of movement after movement has lost its shape. Why water behaves like it has a memory, but not the way myths claim. Water does not remember your words, your emotions, or a blessing whispered above a glass, but it absolutely carries histories written in chemistry, temperature, minerals, pressure, pollution, motion, and the places it has touched. This is where the mystery becomes more interesting than the myth. You may have heard claims that water has a special memory, that it can store intentions, that it can remember substances long after they are gone, or that kind words can change its structure into beautiful crystals, while harsh words make it ugly. These ideas are popular because they feel poetic, intimate, and emotionally satisfying, but they are not supported by reliable science in the way they are often presented. Liquid water is not a tape recorder for thoughts. Its molecules are constantly moving, rotating, forming and breaking hydrogen bonds at incredibly fast timescales. The local arrangement around any one molecule changes so quickly that a stable memory of a spoken sentence or distant emotional state does not survive in the liquid as a meaningful structure. If water truly stored every influence in that simple, mystical way, every glass would be an unreadable archive of pipes, oceans, clouds, rivers, stomachs, stones, factories, sunlight, storms, and hands. It would not be a clean spiritual message. It would be chaos. But rejecting the myth does not make water boring. It makes water more honest, and the honest version is astonishing. Water remembers in ways that are physical, measurable, and real. A river remembers the mountains it crossed through dissolved minerals. Groundwater remembers the rock layers it filtered through, sometimes carrying calcium, magnesium, iron, salt, sulfur compounds, or trace elements that change its taste, hardness, and behavior. Rainwater remembers the atmosphere it fell through, gathering tiny amounts of dust, gases, and pollutants along the way. Ocean water remembers evaporation and freezing through its saltiness. Glaciers remember ancient climates in layers of trapped air bubbles and oxygen isotope ratios, allowing scientists to reconstruct parts of Earth's past from ice cores. A lake can remember a season of heat through stratification, where warmer water sits above colder, deeper water, changing oxygen levels and affecting fish, algae, and microbes. A cup of boiled water may taste slightly different after cooling because dissolved gases were driven out. A kettle remembers hard water through limescale left behind as minerals build up on its surface. A pipe remembers years of flow through corrosion, deposits, and biofilms. This is not magical memory. It is material history. Water carries what it dissolves, suspends, warms, cools, erodes, deposits, and exchanges. Its memory is not a hidden consciousness. It is evidence. And because water is such a powerful solvent, this evidence can be incredibly rich. Pure water, in the strict chemical sense, is rare outside laboratories because water is always interacting. It pulls ions from minerals, absorbs gases from air, carries organic molecules from soil, transports nutrients through plants, moves waste through bodies, shapes coastlines, and redistributes heat across the planet. When people call water the universal solvent, they do not mean it dissolves everything, but they mean it dissolves many more substances than most liquids do. That is one reason it is so important for life. Inside your body, water is not just background fluid. It is the medium where ions move, proteins fold, chemical reactions happen, nutrients travel, waste is carried away, and cells maintain their inner conditions. But again, this is not mystical memory. It is molecular usefulness. Water's polarity, its uneven distribution of electrical charge, makes it good at surrounding charged particles and helping them separate. That same property helps salt dissolve, helps blood carry substances, helps cells function, and helps weathering slowly break down rocks. In this sense, water is less like a diary of emotions and more like a messenger that constantly picks up traces from the world. It does not remember by holding a fixed shape. It remembers by changing composition. If you test water from different places, you can often learn where it has been. Scientists can study isotopes in water to understand rainfall patterns, evaporation, altitude, temperature history, and the movement of groundwater. They can analyze contaminants to trace industrial pollution or agricultural runoff. They can measure salinity to understand mixing between fresh and ocean water. They can detect microbial communities that reveal environmental conditions. The water itself becomes a clue. A drop from a glacier, a cave, a well, a storm drain, a rainforest leaf, and a human tear may all look clear, but chemically they are not identical. Each has been shaped by a path. This is the real memory of water. Not a spiritual recording, but a physical fingerprint. There is also short-term memory in the loose everyday sense when water carries motion. Stir a glass, and the swirling continues for a while after your hand stops. Pour water into a basin, and ripples spread outward, reflect from the edges, overlap, and fade. Warm one side of a container and internal currents may continue moving after the heat source changes. Freeze water, and the crystal structure of ice preserves a moment of phase change far longer than the liquid could. Snow, frost, ice layers, and bubbles trapped in frozen water can store environmental information because solid ice locks things in place much more effectively than liquid water. Liquid forgets structure quickly, ice can preserve. That difference matters. Many myths about water memory blur liquid and crystal behavior, or confuse the beauty of frozen patterns with proof of emotional storage. Ice crystals can form different shapes depending on temperature, impurities, freezing rate, vibration, surface conditions, and many uncontrolled variables. Beautiful crystals do not prove that water understood kindness. Broken or irregular crystals do not prove that water absorbed hate. Real experiments need controls, repeatability, blinding, and careful measurement, not selected images that match a story we already want to believe. And this may be the most important lesson. Wonder does not need falsehood to survive. You do not have to claim that water listens to thoughts in order to see that it is deeply connected to life, climate, geology, and memory in the scientific sense. The rain falling today may have evaporated from an ocean, crossed a continent, entered a river, passed through a plant, frozen in a cloud, melted again, and joined a glass in your hand. The molecules themselves may have been part of countless cycles over deep time, but not as conscious witnesses, not as tiny historians carrying emotional scenes, more like travelers in an endless planetary circulation. Water changes form, changes place, changes partners. It becomes vapor, cloud, rain, river, blood, sap, ice, ocean, mist. It does not keep a stable personal memory of each form, but the systems it moves through often keep records because of what water leaves behind or carries forward. A canyon is water's memory carved into stone. A mineral deposit is water's memory written as crust. A floodplain is water's memory spread across land. A rusted pipe is water's memory in metal. A glacier is water's memory frozen into time. Your own body, mostly water by mass, is not a mystical vessel of messages, but a living chemistry made possible because water is so good at dissolving, transporting, cushioning, cooling, and reacting. The myth says water is magical because it can hear us. The science says water is extraordinary because it connects almost everything without needing to hear anything. It does not need consciousness to shape continents. It does not need emotion to carry minerals from mountains to sea. It does not need intention to hold traces of pollution, climate, salt, soil, and life. So the next time someone says water has memory, pause before accepting the easy version or rejecting the whole idea too quickly. Ask what kind of memory they mean. If they mean a glass of water storing spoken words as hidden structure, the evidence does not support it. If they mean water preserving the physical consequences of its journey, then yes, water is one of the greatest record keepers on Earth. Not because it thinks, but because it touches everything, dissolves part of what it touches, and carries those traces onward. The truth is quieter than the myth, but deeper. Water does not remember like a mind. It remembers like a riverbed, like an ice core, like a stain, like a mineral ring, like a chemical signature, like a path that changes every place it passes through. And perhaps that is enough. Perhaps the real wonder is not that water listens to us, but that it has been speaking in evidence all along. The invisible rules that make the ordinary world work. Nothing in your day is as casual as it looks. Every ordinary moment is being held together by rules so quiet, so consistent, and so deeply built into the world that your mind stops noticing them. A spoon rests on a table, steam rises from tea, a door closes, a tire grips the road, rain gathers in a gutter, bread browns in an oven, and your brain calls these things normal, as if normal means empty of mystery. But normal is often just mystery that has repeated itself enough times to feel safe. The ordinary world works because matter responds to forces. Energy changes form without simply disappearing. Heat moves through materials. Pressure tries to even itself out. Structures carry stress until they cannot, and small differences create motion wherever nature allows them to relax. You do not need to understand all of this to pour water into a glass or walk across a floor. But these actions only feel simple because the rules beneath them are dependable. When you place your cup down, the table does not decide to hold it. The material inside the table resists deformation. The floor supports the table. Gravity pulls everything downward, and the atoms in each object resist being pushed into the same space. Your experience is just the cup stays there. But beneath that stillness is a layered agreement between force, structure, and resistance. The same hidden logic appears when you walk. You think you are simply moving your legs, but each step depends on friction between your shoe and the ground. Without enough friction, the ground cannot push you forward properly, and your foot slips. With enough friction, your backward push becomes forward motion. Walking is not just balance and muscle, it is a negotiation with the surface beneath you. A smooth, icy path, a rubber sole, a dusty floor, and wet tile all change that negotiation. The invisible rule is always there. Motion depends not only on effort, but on the conditions that allow effort to become movement. Heat follows another quiet rule. It tends to move from warmer regions toward cooler ones, which is why hot coffee cools in a room, why a metal spoon warms quickly in soup, and why a blanket does not create heat by itself but slows the escape of warmth from your body. The world is full of these transfers. A refrigerator moves heat out of its interior. A radiator spreads warmth into air. A pan carries energy into food. A sunlit wall stores heat and releases it later. Every warm or cold sensation is part of a larger flow of energy-seeking balance. Pressure works in a similar way. Open a sealed bottle of fizzy drink, and gas rushes out because pressure inside was higher than outside. Wind blows because air moves from regions of higher pressure toward lower pressure, shaped by Earth's rotation, temperature differences, and landscape. Water flows downhill because gravity gives it a direction, but pipes, valves, pumps, and channels guide that flow into useful paths. Much of civilization is built from hidden rules turned into tools. Wheels reduce dragging, levers multiply force, pulleys redirect effort, gears trade speed for strength, lenses bend light, circuits guide charge, insulation slows heat, and springs store energy by changing shape. Human technology does not escape physics. It succeeds by cooperating with it. Even living things are not exceptions. Your body works because it maintains carefully controlled differences. Oxygen here, carbon dioxide there, more salt outside one cell region, less inside another. Warmth kept within a narrow range, pressure changing with each breath, electrical signals moving through nerves. Life is not a break from physical law. It is physical law organized with astonishing precision. A heartbeat is a timed mechanical wave through muscle. A breath is pressure and gas exchange. Digestion is chemistry guided by shape, temperature, and enzymes. Vision is light translated into nerve activity. The ordinary miracle of being alive is that countless processes keep correcting themselves before you notice anything is wrong. This is called feedback, and it is one of the great invisible rules behind stability. Your body cools itself by sweating, warms itself by shivering, adjusts pupil size to light, and changes heart rate when activity increases. Machines use feedback too. Thermostats, engines, cameras, elevators, and airplanes all depend on systems that sense change and respond. Without feedback, small errors can grow. With feedback, disorder can be controlled for a while. But the world also has thresholds. And this is where the ordinary can suddenly become dramatic. A branch bends and bends, then snaps. Water heats quietly, then boils. A pile of sand grows grain by grain, then slides. A stretched fabric holds, then tears. A storm gathers moisture and charge, then releases rain or lightning. The final moment looks sudden only because the preparation was hidden. This is one of the most important lessons the ordinary world teaches. Silence does not always mean nothing is happening. Sometimes stress is accumulating. Sometimes energy is being stored. Sometimes a system is moving toward a boundary you cannot see. What feels like an instant event may be the visible ending of a long, invisible process. And still, these rules do not make the world cold or mechanical in a lifeless way. They make it more intimate. They show that every familiar object is participating in a deeper order. A glass is not just glass. It is a material that transmits some light, reflects some, resists some forces, breaks under certain stresses, expands with heat, and carries the memory of how it cooled into shape. A flame is not just brightness. It is chemistry releasing energy, heating air, producing light, consuming fuel, and changing everything it touches. A cloud is not just softness. It is water, temperature, pressure, and air motion made visible. A road is not just a surface. It is friction, load, expansion, drainage, and material strength working together. The world feels ordinary because your brain compresses all of this into simple labels: table, cup, floor, rain, heat, light, sound. But science opens those labels and shows you the hidden agreements inside them. The most beautiful part is that these rules do not need to be dramatic to be profound. A hinge turning, a droplet falling, a wheel rolling, a shadow shifting, a match lighting, a seed pushing through soil, all are small events where invisible laws become visible behavior. The ordinary world works because it is not random in every direction. It has tendencies, it has limits. It has balances, flows, resistances, and transformations. It gives you enough reliability to live, build, cook, travel, heal, and predict. And perhaps that reliability is the miracle we overlook most often. The universe does not need to surprise you every second to be astonishing. Sometimes its deepest wonder is that the floor keeps holding, the air keeps flowing, the light keeps arriving, the body keeps adjusting, and matter keeps answering the same quiet rules with endless new forms. So the next time a day feels plain, look again. The ordinary is not empty. It is a hidden system behaving beautifully enough for you to forget how much is happening.